Test, test, test. Yeah.
Test. Good morning, everyone. We'll just give a couple of minutes for the rest of the people to arrive. Maybe after yesterday's drinking spree, people are needing a little bit of more time to get ready. So don't worry, it will start soon. Okay, so let's get started. So first of all, I'm going to introduce myself. I'm Leonardo Cardoso. I'm one of the previous organizers for all of the previous sessions. Thank you. Don't just applaud me. There's Jean-Michel Friet, Hervé Bauglen, Cyril Morin, and also Thomas Lavarenne, who couldn't be here today. We have been carrying on the flame for the GNU Radio European Days for a couple of years now, actually. And I would like to take the opportunity, actually, to address our next one, which has yet to be decided, by the way. We are actually open for anyone who is willing to host it in their own place. So it's European, can be in any country in Europe, not just in France as the previous ones. Actually, we're very happy for Ralph, and I think he really deserves an applause because he actually took on all the load of doing this here, which I'm pretty sure wasn't not very easy, but pleasurable, I hope. And so the idea is that actually we talk about this by the end of the day. We're not yet sure exactly when that will happen, but for those of you who are interested in maybe hosting the next European GNU Radio Days in your place, don't worry, you'll be helped by all of us, by the previous organizers. We have a lot of experience on that, so we'll help you out. It will happen by the end of the day. At some point, we will decide. We're not yet sure, but we'll discuss with Ralph, and then we'll make an announcement. So, reminding us of our schedule today, we'll have our keynote talk. During the keynote talk, there's going to be a question and answer session. After that, we're going for the coffee break. Then there are going to be two contributed talks. And then we're going for the lightning talks. Then lunch break as usual. And then in the afternoon, there's a couple of changes, so I will try to address this right now. On the website, the dev tutorial and the non-dev tutorial, right? So the dev tutorial is going to happen right here in this room from 13:30 to 15. It's just going to be one dev tutorial. The other one actually has moved to Friday. And for the non-dev tutorial, you're seeing something around 45 minutes on the website. It's actually going to be 1 hour and a half, just like the dev tutorial. And then you'll have time for the coffee break, and then to come back to this room here for the guided tutorials in the end. Just one thing, so the non-dev tutorial was going to be given by, once again, Jean-Michel Friet at the other room, which is on the entrance of the building. And the title is also wrong. As far as I understood by Jean-Michel Friet, is going to concern actually how to connect new radios with other kinds of devices. So that might be interesting to some people. If you're interested in that, well, you know where to go now. And then, well, coffee break, and then developer guided tutorials in the end, up until 17 when we finish the day. And then maybe afterwards, as I said, we will have a discussion with everyone who wants to participate about what we're going to do for next year. All right? So right now, I would like to invite to the stage Josh Mormon, who is the president of GNU Radio. So he's going to talk about the GNU Radio project, the overview, and updates. Please a hand to Josh.
All right, thank you. All right. Let's see. Oops. Go. All right, thank you. And I just want to echo the big thank you to Ralph and everyone here at FAIR for hosting this event. So this is the tours yesterday were incredible to see. Just the magnitude of what's going on and how GNU Radio is being integrated into that is very informative and interesting. I've never seen anything like that, so so thank you. So my name's Josh. So I'm a member of the GNU Radio board, currently serving as the president, and I want to bring an update of the project. And so a lot of the talk this week has been focused on GNU Radio 4.0. So I want to bring it back to kind of the current state of GNU Radio and how we bring 4.0 into the community as broader adoption. So first we have to ask ourselves a question: what is GNU Radio, and what makes GNU Radio kind of special as an SDR framework? So we heard some of this from Eric the other day in terms of where GNU Radio came from, and so I want to kind of address it as to what the current state of the project is. So GNU Radio, is it an SDR application? Not really. So GNU Radio, it's not something that we can just ship as an application and say, here's GNU Radio, and then hot swap it in with something else. This is GNU Radio now. It enables all sorts of applications. Particle accelerators, digitizing in that context being one of them. But as it is an SDR framework, the biggest part of GNU Radio is that it is a framework, a community, and altogether that, an ecosystem. So there's a lot of factors to consider when we talk about GNU Radio that make it something very special in terms of software-defined radio. Where is GNU Radio used? So particle accelerators was something that was never on my radar when I first started using GNU Radio. So traditionally, the wireless communications realm is where people think of GNU Radio being used. How do you send, receive signals? There's heavy usage in amateur radio. There's a big user base in radio astronomy, space communications, everywhere imaginable where signals are being sent and received over the air, or anything that's digitized needs signal processing in a block-based graph model. If you do a quick search on Google Scholar, if you just search GNU Radio, you'll see all sorts of things you couldn't imagine where GNU Radio is being used. Yeah, a few examples, and then this list goes on. There's thousands of papers published every year about using GNU Radio, SDR. But I want to talk a bit more broadly about the GNU Radio ecosystem and the community. So GNU Radio, let's see, I don't know, there's no pointer here. But GNU Radio, so we have organized in a way, so in the last, maybe 4 or 5 years ago, we shifted from, I guess, what Eric described as the benevolent dictator model to a more structured organization. And as we move further away from the initial group of people that created the software, it's very important to make sure that we have a sustainable leadership going forward. So the way we're structured is we have the General Assembly, we have a 3-person board, and a General Assembly which is not bounded by size. So the General Assembly is a group of people who meet together every so often, a couple times a month, and talk about the current state of GNU Radio, help set the priorities, and then also elect the board. And the board is responsible for the finances of the organization, for what we're going to do with our technical priorities, non-technical priorities. And we are also fiscally associated with, perfect, thank you. Let's see, and then this clicks here, perfect. So we are incorporated under the SETI Institute, so they manage all our finances and logistics. So that has enabled us to have a partner in acquiring grants, managing logistics of our money, of our finances, because GNU Radio, if you're not aware, is an all-volunteer organization. We don't have within ourselves a paid staff. It's a grouping of, the leadership is a grouping of people with varied interests, and they're all there for very different reasons. Some people are enthusiasts about just loving radio, loving working on the software. Others are there because it associates well with their job. But it's a very diverse group of people. So in a structural sense, we organize ourselves around teams. And these teams might be, say, the GRC team. It might be the 4.0 development architecture working group team. There might be interest groups, such as the amateur radio interest group. And these are things that are kind of ad hoc, and mostly we work together on our chat server. So if you've never gotten onto chat.gnuradio.org, that's really where most of the activity takes place. So in terms of organization, that is really where we consider GNU Radio, where the decisions are made. Now, the broader ecosystem, there's a lot of people that aren't necessarily part of the leadership of GNU Radio, but do extremely important work in the community, such as, I'll highlight here, distribution packaging. So something that's happened over the last, 5 years or so is the ability to just go into your Ubuntu install and just say apt install GNU Radio. A ton of work went into making that happen. A ton of coordination with the maintainer. So I think, Marcus, you got our earlier releases to the point where they could be packaged in that way. Yes. but Maitland Bottoms, who does that effort on the Debian side, and then these roll into Ubuntu. There is Ryan Voles, who works at Haystack Observatory, puts together all the Conda releases. And this enables GNU Radio to be very easily installed on Windows and Mac within the Conda framework. And then, Fedora, any Linux installation, there's somebody that is doing the effort to make sure GNU Radio stays up to date on those. And that is something that really we don't even have visibility into all the different packaging. So these are just people in the community that help out and make that happen. We also have we do GNU Radio Conference and many events throughout the year, so we have organizers involved in that. And such as this event and the EU GR Days. and then also from a technical standpoint, the code base. The code base is kind of shepherded by a group of maintainers, and we'll talk a bit more about that in a minute. But from a technical standpoint, that is done again on an all-volunteer basis. Another important, and I think back to the original question of what makes GNU Radio so special, the ecosystem of out-of-tree modules. You can go out onto the internet and find an out-of-tree module that does something that you might be interested in, something you didn't even know about, but there's all these out-of-tree modules managed by individuals that keep them up to date, and we try to archive them on cgran.org. But again, that's, as an open source project, you don't quite have visibility into everything, so that is just a kind of an ecosystem unto itself. All of our communication methods, chat, tutorials, which there's been a lot of effort over the last couple of years to update those tutorials with the latest versions of GNU Radio and make the examples up to date. So a lot of work has gone into that. We have our website, the wiki, and then the mailing list, and also our social media. And then also, part of the GNU Radio ecosystem is projects that are affiliated with GNU Radio or are built on top of GNU Radio, such as you might be familiar with GQRX. Some of the newer ones like IQ Engine aren't necessarily GNU Radio based, but they store data in the SIGMF format, which is a metadata format for storing IQ recordings that was kind of born out of the GNU Radio community. So there's a lot of different projects that are affiliated with GNU Radio, but not specifically part of our community. So just kind of want to give a broad view of the ecosystem of GNU Radio. This button. All right. So in terms of leadership, as I mentioned, we have a 3-person board. Currently, I'm serving as the president. But the board is elected by the General Assembly. The General Assembly is a group of people that have some sort of leadership position in the community. For instance, Jean-Michel Friet is a leader in the academic outreach and the organization of this conference. And he's a vital member of the GA because he has insight into a big part of the community here. So the General Assembly, just to give you an idea, is 12, 13 people right now, but it's not bounded. And we do look to expand the GA as people take on more leadership areas in the community. We also, another key position in the leadership is the SETI PI. So we are financially organized under SETI. And so Derek Kozel serves as the principal investigator with SETI to help manage that interface, help bring in grants, manage our contracts, things like that. So then also there's various technical roles, community roles. So that's just a general overview of how our leadership is structured. It's not, I'm not in charge of the project. There's a lot of people that have various levels of involvement. So I like to joke about the title president, but it's not a super powerful, bang my hammer type of position here. And the SETI Institute, so they are our partners, and they've been a great partner here. They help us, they give us inroads into various avenues of development, application, education. They manage a lot of logistics, help us gain access to grants and educational outreach. So I want to talk a bit about the current state of GR3. Before we talk at all about GR4, I want to say where GR3 has gone over the last year, where it's going. Still things that we want to do there, because when we talk about GNU Radio, when most people think about GNU Radio, it is GR3. So thanks to very active maintenance by Jeff Long and Marcus and others that are involved in the maintenance team, over the last couple of years, you've seen very consistent GNU Radio releases happening every quarter or so. And this is thanks to ongoing hard work from that team. And one of the things I want to highlight is this release right here, 3.10.9, made it into Ubuntu 24.04. So there's some timing involved in there to where, you get everything lined up perfectly and it rolls into Ubuntu, and then now folks can just apt install GNU Radio in Ubuntu and have a very up-to-date version. So that is quite an impressive feat. Then, when I first started working on GNU Radio, you had pi bombs, and it was not the easiest thing to get GNU Radio running. We also have had several Volk releases over the last year or so, thanks to Johannes as the maintainer of that project. So say hi to Johannes. But one thing I would like to highlight here is that GNU Radio is looking for additional maintainers. So maintenance is done as a team effort. If you are interested in getting involved in that, so if there's a piece of the code base that you're specifically passionate about or know something about and would like to really focus on the pull requests that come in there and kind of own that module, I'd love to hear from you and see more people get involved there. Our goal, well, not our goal. I'd say the reality of the situation is we probably will reduce the number of maintenance releases. So they've been coming about every quarter. We plan on bringing that down just a little bit because the number of things that have been added and fixed over the last year has been slowing a bit, which is a good problem. Most of the things coming in right now have been focused on the new GRC Qt and getting that up to feature parity with the traditional GRC. So, but any help, if anyone's interested in helping with release management, rolling out releases, maybe 2-3 times a year instead of 4 times a year, that would be greatly appreciated. So email us if you are interested in any capacity here. So let's talk about some of the things from a development standpoint that have been happening very recently. So most of the development work on GNU Radio has happened thanks to a generous grant from ARDC, which is the Amateur Radio Digital Communications Organization. So we got this grant we applied for and received this grant from ARDC about 2.5 years ago, and a substantial grant focused on the usability enhancements in GNU Radio. So GNU Radio as a framework, it's only useful to a broader group of people if it's usable and accessible, and so that was the goal of this funding. So some of the things that have happened under this funding, one is the ability to install GNU Radio and out-of-tree modules using native installers. So right now, you can install GNU Radio in Windows through Conda. That's not necessarily accessible, say, in an educational setting. But the ability to just download, GNURadio.msi and let's say grwifi.msi and install those just like you would any other Windows program. So that's the goal of making these installation packages of GNU Radio and out-of-tree for both Windows and Mac. So that work is wrapping up, and we hope to have an announcement soon on that to where you can just go to GNURadio.org, download the installation packages, double-click on them, and be able to install GNU Radio that way. Ongoing software maintenance and support. Of course, things get backed up in our issues and PR log, and so Marcus was able to thrash the issue tracker there to triage everything that was in, say, you know what, we're not going to fix this, we're deferring this to 4.0, so be able to make a lot of decisions, categorize things to where we can point people in the right direction and say, yes, this is where we need help with. No, these are issues that are great for first-time contributors, things like that. And then also some of the low-hanging fruit, just go ahead and fix it. So thanks to Marcus, we were able to make a lot of progress and clean up the issue tracker in that way. Yes. So one of the big efforts here on this grant was beginning the process of updating GNU Radio Companion to be based on Qt instead of GTK. So GTK, I guess kind of an ongoing problem with an open source project with dependencies is that as time goes on, some of these dependencies become more and more unwieldy. GTK is one of those, so that's one of the more difficult things to package and manage in GNU Radio. So getting it up to using Qt as the graphical front end became a priority. The other thing that Qt enables is it enables GRC to be able to run under WebAssembly in a browser. So that was shown at some point, I think before this effort really kicked off. But if you take the current main branch of GNU Radio, so not the version that showed up in Ubuntu recently, but the current main branch of GNU Radio, and you run GNU Radio to companion --Qt, you'll see the Qt version of GNU Radio. So it is not quite up to feature parity, but it's getting there, and that is the path forward. So again, if you're a Python person and you're interested in getting involved in contributing some code, that is a great place to help out and add things. Another effort is ongoing updating of our tutorials. So when people first start using GNU Radio, it's like, well, what do I do with this thing? Here's GRC. I've got a whole bunch of blocks. I want to write my own blocks. Our tutorials had gotten out of date as GNU Radio had transitioned over time from, say, 3.7 to 3.10. A lot of the blocks that were used in the tutorials had become deprecated. So Wavewalker DSP went through and updated all of our tutorials and the example flow graphs to match the current state of GNU Radio. So just kind of important ongoing maintenance of our documentation. And then related to that, Bailey Campbell is in the process of updating our documentation infrastructure. So right now we have a lot of information on the wiki, and we have a lot of stuff in the code in Doxygen, and those are kind of two separate worlds. And so the goal here is to bring it all together and have versioned documentation through the CI that comes out and can show up on readthedocs.io. So just kind of modernizing our documentation infrastructure there. And then the last piece of this, we had a bit of funding left at the end of this, and the whole goal is GNU Radio usability enhancements. And looking forward to GR4, we want GR4 to be usable. So this is where Danny Estevez started working with us, and I will not talk too much about this because he has the next presentation, I believe. But having a documented example of something that people do in GNU Radio, but using the GNU Radio 4.0 code base. So that I will leave that to Danny to talk more about. So just a little more, not too much detail here, but yeah, the Qt version of GRC, it is there. It continually gets better. So the screenshot might not look great because this is from a few months ago. But yeah, the idea is it is exactly the same thing visually as GRC, just running with Qt instead of GTK. So another area where we get additional development effort is through Google Summer of Code program. So this year, we fortunately had 2 GSOC students. We had Kayla Comer and Zaki Hermelon. So Kayla Comer worked on beefing up our grFEC package. I believe this was adding affect as a way to do the LDPC coding, and just generally overhauling and improving our grFEC. So thank you to Andre, Danny, I believe Marcus, Johannes, you're probably involved in this as well. And then Zaki, so the goal of this is to take GRC. So there's a lot of potential for GRC as a front end to do a lot more things rather than just render a GNU Radio flow graph. So the effort here is to kind of modularize GRC and enable custom workflows that I can say, I might not just want, you have a few choices in GRC. You can, make your blocks render to you can make it render to a Qt type of flow graph. You can render to a C++ program. So there might be more things. So modularize that and have a type of workflow. I might want to render it to use some other graphical library, things like that. And so thanks to Zaki, but also thanks to Sebastian and Hakan for mentoring there. And also, we'll keep in mind, we'll make announcements. The next round of GSOC, that happens in the spring when we start announcing that. So spring or summer? May, yeah. So yeah. We go through this every year. So yeah, keep your ears open. If you know students that would be interested in this. So what else do we want to do with GR3? We don't want it to become a stale project. We want to continually add things, make it better, make it more stable. So just some things that in the board and leadership we've talked about that are kind of on our view here. One is SIGMF integration. I think SIGMF is a great addition to the overall SDR ecosystem. It is. How many people in here are familiar with SIGMF? Show of hands, about half? Okay, cool. So if you're not familiar with SIGMF, it is a metadata format for RF radio recordings, or for any type of RF IQ data. There's a lot of different things you could do with it, but it enables you to describe, to have the binary data of the capture or captures, and then have the metadata right along with it in a way that's very portable, very simple, and we see this becoming standardized in a lot of areas. And so having that kind of natively as the way of recording data within GNU Radio, that's a very high priority for us, because the whole format originated out of the GNU Radio community. Another thing that we definitely would like to improve going forward is the aesthetics of our graphical widgets. So we have these if you run a flow graph and you put a waterfall plot there, we have these Qt widgets, and there's lots of options for doing different types of visualization here. So even just within GNU Radio, we could probably make these prettier. They look a little bit older. We talked about the native installers for Windows and Mac. That gives us a lot more avenues for accessibility into different communities if we're able to very easily install on Windows and Mac. Again, also documentation infrastructure, GRC Qt, really getting that up to feature parity so we can eventually drop the GTK dependency is highly desired. And then as part of our CI, right now we do unit testing of all the modules in the CI, but it would be nice if we could get more integrated tests across modules, running data through, say, our FEC encoders through an entire digital comms chain inside our CI. And then another piece of this that has been talked about a lot in the organization is improvements to CGRAN. So right now, if you go to cgran.org, you'll see a big list of out-of-tree modules, but the state of those is kind of, it's unknown. It varies how long ago they were updated. But being able to track that more closely, perhaps have a curated list of out-of-tree modules in the community, that's something that we could probably do a better job at and will work towards over the next, in the near future. All right, and something I should mention here is some of these do apply to both GR3X and 4.0. Holistically, these are things we should be keeping our eye on. So I want to bring out a vision for the project that we have discussed within the board, things we want to focus on, and start to talk about how 4.0 fits into all of this. So our vision generally is to strengthen the project, spread the project, sustain the project. I apologize for the alliteration, but really these three aspects are where we want to go to make GNU Radio last for the next 20 years and beyond that. So strengthen, what do I mean by that? What we want to do is we want to continually improve GNU. Some of this might be a bit obvious, right? We want to make GNU Radio better. We want to make it stronger. We want to make it more feature-rich. But really, the purpose here, we want to maintain GNU Radio's position. We want our standing as the leading open source SDR framework for rapid prototyping and real-time signal processing applications. So we want to expand the usability of GNU Radio in scenarios where people might not be using it right now. So we want to make this code base as strong, stable, performant as possible. So this is one aspect of the vision. And why? GNU Radio enables innovation in scientific applications. So we want to be a part of that. We want GNU Radio to be a component where we say, this is where you can do your signal processing in a very accessible way. We would also like to spread the footprint of GNU Radio. So one place where we'd like to spread it more, where where we see some usage, we see GNU Radio being used in educational programs at universities, but we think there could be more. And it'd be good. Please come talk to me. I'd love to have these conversations about how we can get GNU Radio as a part of more university courses, as a part of even community college, high school. Somebody I was chatting with on the GNU Radio chat is actually using GNU Radio in a primary school with fourth graders. So I haven't followed back up. That was a couple months ago. So I'm curious how that went. It was a pilot program, but hey, if GNU Radio is a tool that can be used at that level, that would be fantastic. We want to prepare the next generation of signal processing engineers, even starting at fourth grade, right? But we want people to have that feel for doing real-time signal processing. Learn the fundamentals, maybe using MATLAB and Python, but then move to that next step of doing real-time signal processing and getting a feel for that in their university courses. So how can we as an organization enable our partners in universities? How can we build a bigger network in the academic community? And so part of that, part of some of the things that I've heard is, one, being able to run more easily on Windows devices. That's something that, in academics, that academic communities, that is there, but also keeping GNU Radio usability for beginners, installation methods, et cetera. Another thing that we know we suck at marketing. As an organization, we do our best, but we're not out there with really shiny emails and marketing. We have our mailing list, we have our chat server. That's definitely something that we could do. Are there a lot of people we're not reaching because we're not marketing the right way? We're not marketing how you should be marketing in 2024. So are there more people we could be reaching and say, hey, GNU Radio does this thing, and people can identify that and say, oh, I'm doing that thing. I could use GNU Radio rather than coding something up on my own. And then that's also training opportunities too, where we can identify the people that might be wanting to use GNU Radio, but there's that gap between, well, how do I actually get this into my ecosystem? So we can put them in contact with the right people. We can build up the training materials. And again, we have to ask ourselves, why is this part of the vision? Without this shared framework, we do lead to this fractured ecosystem. We want as many people using the tools as possible, because then the tools get better and better, rather than kind of, broken up, everyone reinventing the wheel every time. So in terms of, we're talking about the spread of GNU Radio. One of the challenges we have is it's hard to quantify how much GNU Radio is out there. So we have some insights into it, but we don't put tracking cookies on our website. We don't track our emails, things like that. So how can we know how many people are using GNU Radio? Well, one, we can look at various, like this is a plot of Google Scholar. How many publications over the years have used the term GNU Radio? So it's up over 1,000, and it's hovered around there. It's hard to keep up to date. So thank you for Jean-Michel for helping with this analysis. And in various ways you look at it, the numbers are different. But definitely there's a healthy number of academic publications using GNU Radio that make it onto Google Scholar. That's a little bit delayed, so this goes up to 2023. But it definitely has stayed healthy over the years and grown over time. Another one, this is visits to our GitHub repo. So it's just random week in August, there were 4,000 unique visitors to our GitHub repo. And then Conda Forge, so that's another, one of the newer ways that people can get and access GNU Radio. Now this here, it says 1 million total downloads. I don't know if I believe that number, or I think that's probably a lot of automated infrastructure, maybe bots, who knows. But there still seems to be a lot of people downloading GNU Radio from the Conda packaging, which is great because a lot of work has gone into getting that integrated into our CI, and thanks to Ryan at Haystack for maintaining that very actively. So the third part of our vision here is to sustain the organization, sustain the project, both financially and in terms of leadership. So one, future-proof the leadership of the organization. So we want to continually build the leadership team. It can be a great opportunity, especially for developing professionals, to be involved in the project. There's opportunities to help with the maintenance team, to help in all aspects of the project, and yes, it's a great opportunity. It's definitely helped me in my career, being deeply involved in GNU Radio, and I think it opens up a lot of opportunities for people in their career. There's a lot of networking opportunities, so on and so forth. But as an organization, we want to move a bit beyond an all-volunteer organization. One of the things, so in terms of funding, so we're aligned with SETI Institute. But really, the avenues for funding for GNU Radio right now come out of GNU Radio Conference. We get a little bit of funding that way, and what we're trying to do, where we would like to get to, so just being completely transparent, is we would like to have some paid administrative program management support, and to be able to have the ongoing funding to support that. So what we are looking at, and we're going to announce at GRCon, is an industry and government partnership program. So the details will be laid out in the next month or so. But yeah, so stay tuned for that. But then there's also, GNU Radio gets development work done, mostly by people that are funded external development efforts. Ralph and his team at FAIR are a great example of this. There's a need, there's an identity, there's identification that GNU Radio fits a need, and if we can add this into the framework rather than just doing it ourselves, then it benefits everyone. So external development efforts are really how a lot of things have gotten done over the years. And one example of this, which I'll highlight a bit more in a bit, is there was a DARPA SDR 4.0 program, and this was done to add some specific features to GNU Radio that I'll talk about in a minute, but government-funded efforts, yes, are a great way to do much larger scale things than we can do with the smaller amounts of money that come in directly through GNU Radio. So why do we want to sustain the organization? Well, we want to maintain a healthy ecosystem, and having this cohesive organization, helps us to kind of keep our tabs on what's going on and make better decisions as a community and for the community. So now let's get to the exciting part. We're going to talk a bit about how 4.0, how do we get to 4.0? So first let's start, how do we get from GNU Radio 3 to where we're at talking about 4.0. So a brief history of 4.0. So look at this from a positive standpoint first. So got the negatives down here at the bottom. Let's look at the positive first. People want to do more with GNU Radio. So GNU Radio solves a lot of problems, a lot of very different problems for a lot of people. And there's a lot of people that are kind of pushing the bounds of GNU Radio. So moving beyond some of those limitations is something that people have talked about for years and years. So I'll identify some of the pain points that people have identified. And one is this fixed scheduling. Having the thread per block scheduling, it works great under a whatever percentage of use cases. It's enough. It's great. It's simple. But if you want to really game the performance of your computer running GNU Radio, it might not be ideal. Packetized asynchronous data processing, that was a mechanism that was added at some point and is not quite as optimized as the streaming mechanism. Effective use of hardware accelerators, general ease of use, having less boilerplate, different your documentation in different parts, and then also our ability to work on heterogeneous and distributed platforms. So we have to balance all of this, anything that we're going to fix, with one framework can't solve everyone's problem. So really our theme for the last several years has been modularity. That's what we want 4.0, is to be a modular solution to where we don't want to solve everyone's problem for everybody, but we want to carve out the places where there's something specific. You need something scheduled in a certain way. You need some real-time, low-latency scheduling. Well, you can develop a scheduler for that. So I'm jumping ahead a little bit. So let's get back to the history. So the first I really started getting involved or aware of the push towards a new GNU Radio, or a next big thing, was the work that Bastian and Marcus did towards benchmarking and untangling the scheduler within GNU Radio. So the links are here. Blogs are very they're very thorough. There was a paper published at GRCon. Marcus presented this and really identified quantitatively what are the weak points of GNU Radio and what we should do better. And one of the big things here is the thread per block scheduler. We're leaving a lot of processing on the table by doing all that context switching, especially when you have one thread per block and a lot more blocks than cores. So this was 5 years ago. The next FOSDEM, we got together. There was, several of us got together. This was at ESA in Noordwijk, and really the conclusion going into that was we're going to have to build something from the ground up in order to untangle the scheduler, to do something more modular. And so this led to what we had called for a long time the New Sketch project. It eventually became the Dev 4.0 branch on GNU Radio. So this was generally the same design as GR3, just kind of broken up, more modularized, and then some improvements in usability as well. There were various schedulers. Again, there was a single-threaded scheduler, there was a multi-threaded scheduler, and you could swap them in, and you could set the number of blocks per thread. Now going back to Basti's paper here, so Basti took the GR3 code base. He benchmarked it in a very thorough way and showed how much throughput you could get through a flow graph using however many cores and however many threads you're running, and then in a way that represented what you could do by matching the number of cores and threads, showed that you could get this like 2 or 3x performance boost by doing that. And in this project, we were able to show actually in a GNU Radio-like implementation, something that was on the path to become the next 4.0. We showed this same type of performance improvement. So that was good. Good path. We demonstrated the features at GRCon 2022. Kind of along the way was this SDR 4.0 project, and this was all interrelated, all happening at the same time. So SDR 4.0, again, hitting one of the pain points of GNU Radio is that GNU Radio has had, I should say, this is upstreamed. This made it into the 3.x code base. But at the time, GNU Radio had a kind of a fixed buffering scheme. It would make its own circular buffers, which is still there. And then in order to get into a hardware accelerator, like into a GPU or into the DMA memory of an FPGA, you would have to do that copy. You'd have to ingress into that memory, do your processing on the GPU, go back out into GNU Radio, GNU Radio's buffers, and back in. And that really, you killed the entire benefit of using a hardware accelerator at that point. So this program, the decision was made early on that this would go into 3, but this was one of the key driving factors of GNU Radio 4.0. And the end effect of this of this project, so this was demonstrated and the update given at GRCon 21 is that there is a set of custom buffers that you can, I mean, you can create your own, it's custom, right? But there's an example for CUDA buffers, and what you can do here is you can, say, have your source, you can go into a block that's doing some GPU processing, that's calling CUDA kernels, keep the memory in the GPU, do another GPU processing block, another GPU processing block. And the end result of that is that we get rid of all of this waste of doing the mem copies in and out of the GPU. So this is in 3.10. If you're not aware of this feature and this is useful to you, it is documented on the wiki, wiki.gnuradio.org. Just search custom buffers so you can find out more. But so this was a step towards 4.0. It just happened to get upstreamed into GR3. Now, this feature probably was a lot more effort to get working in GR3 because of various aspects of the history of buffers, things like that. But it's there, and that was a step along the way. But so here's where it starts to get interesting. A couple of years ago, we met Ralph and the team here at FAIR, and so I believe Derek first introduced us to Ralph because GNU Radio was being used very heavily here at FAIR in their digitizers at the accelerator, and we were at this point developing something towards 4.0. It was a very good entry point to add in features that would be helpful for the setup here. And so Ralph engaged very closely with us and started working towards this 4.0 code base. I think specifically for this reflection feature was something that was missing in GNU Radio and would have been something very hard to add into GNU Radio 3. But along the way, as this kind of relationship began to progress, Ralph and the team here identified other things that we could be doing better. We could squeeze even more performance out of these CPUs that are running GNU Radio. And so I'm not going to get into the technical details. That's Ralph's talk and all of these tutorials, but specifically focused on CPU-based processing. We got kind of put this project aside a bit and went full on towards what is now in the code base as GNU Radio 4. So a lot of exciting features that we kind of couldn't do in the microservice architecture, things like block merging and single point of source. So again, this was a very, I would say, unlikely collaboration. Who knew that GNU Radio was used at particle accelerators? I had no idea at the time, but this has turned out to be fantastic for the project. So I would be completely remiss if I did not say how grateful we are as an organization to this engagement with FAIR. The fact that that you guys have become an integral part of this community, and could have done things in a way that only solved your problem, but kind of in the spirit of public money, public code, looked at the broader open source community and said, hey, we can contribute, we can take our stuff and help everybody with it and just help advance scientific innovation more broadly. So yeah, round of applause for Ralph, the team at FAIR. I really... And so Ralph pointed us to this initiative that I was not previously aware of, Public Money, Public Code. So if you have not signed on to this initiative, recommend it. GNU Radio, our logo is there, so we support this cause. It's pretty open. Just code paid by the people should be available to the people, and that is, that is kind of where we're at with this engagement right now. So now, I think the broader question is, how do we get to 4.0 adoption? So that the code base, the 4.0 code base can sit there, it can be used by FAIR, but how do we get this used broader by the community? And not just used broader by the community. We want this to be a community-maintained project like GNU Radio is currently. We want that eventually to become GNU Radio. What is GNU Radio for? Eventually, that's just when you say GNU Radio, that's GNU Radio. The tough part here is that if you look at GNU Radio 3, there's a lot of people that depend on it. There's a lot of, and again, open source project, we don't have entirely great introspection into everyone that's using it, but it's packaged in distributions. People have built applications on it. There's public out-of-tree modules, and then there's an entire user base that uses all of this. And not to this degree, but it starts to look like the classic XKCD, right? You pull out this one Jenga block, the whole thing's going to fall apart. So I look at it this way. So here's a little visual. So we've got GR3 that has kind of evolved over time, and now we've got this big advancement GR4 sitting there, and it's somewhere. There's a summit here that we want to get to, but if you're right here, it looks like a roadblock, right? So here, so this guy, he's the happy GR3 user. He's not performance critical. He's out here, maybe he's just replaying files. Maybe he's just doing an FM radio, right? Teaching it in a university course, not using the full capabilities. And then there's this guy that's really like pushing the boundaries of GR3. And this was me. This is really, I want more. I want that. This is what has led us to talk about GR4 for the last 5-10 years. And then there's all these other people that are kind of left out in the dark. Maybe they don't fit into GR3, but GR4 could be an entry point into the GNU Radio world for whatever reason. Could be licensing. Could be just the way that GNU Radio is installed, all the dependencies or not. So. Really, we have to consider all of these people. Oh, and there's more. Okay. So the question: what will it take to facilitate and accelerate adoption? Obvious statement: benefits outweigh the transition cost. There's going to be transition cost going from a completely rewritten framework from something that that you're used to using and have built your infrastructure around. So right now, what are the most appealing benefits that 4.0 can offer? It varies from person to person. For some, if you're running an RTL SDR on a Raspberry Pi, it's not performance critical. GNU Radio 3.0 might do the job. But we have to consider those people in this. But I think the biggest thing that it will take to accelerate adoption of GR4 is showing the examples of the benefits. And that's why I'm excited about Danny's work. Is going to be the ability to contrast the performance between GR3 and GR4. So with tangible examples, it means more to people than benchmarks, right? You can show that, in this benchmark, I'm going to get so much improvement. Well, it's much more accessible to people to say, hey, I'm running a modem and I can get 4 times the throughput performance. That means a lot more to somebody that might want to fund development towards GNU Radio. And then also there might be new applications enabled by GR4. So we've gotten contacted over the years. People, for various reasons, are unable to use GR3 because of licensing. And I don't get into this talk, but one of the things that really has been enabled by a ground-up development of the GR4 core is a change in the licensing, which could open up the doors for a lot of people that are kind of hamstrung by their lawyers in the GPL, right? Without going too deep into that. So in terms of facilitating adoption, we have to consider the different users. So GRC only users, in theory, you could do a hot swap for them, right? If GRC is the front end, you could swap in whatever's running as long as it's quick enough. But we really have to consider the OOT developers and the people that have built things on top of GR. And the ecosystem is heavily built on out-of-tree modules. So which ones will migrate? How much effort, how much ability for people in the community is there going to be to take what I already have working in GR3 over to GR4? So unfortunately, in the transition from 3.7 to 3.10, you know, there's a lot of modules that did not get updated, and some people went through. I forget the guy's name, but went through and did just module after module after module. But was Bjorn? Okay, yeah, and that was a big effort, very useful effort. But then, not all of that got upstreamed back into the originating repos, so that work sits somewhere not entirely accessible. So, you know, even a small effort, like I think the transition from 3.7 to 3.10 was not, it wasn't a big effort to move your code that way. But a lot of people just didn't want to do it. So we have to think about that. And then the next step, okay, let's say we get to the point where lots of people are using GR4. It's building, we have maintenance of the core, it's become a community-run project. At what point can we say that's now GNU Radio? So I think to become an official GNU Radio release, obviously we have to get up to feature parity, we have to have examples, migration guides, and of course it has to be actively maintained. And I want to make a very strong statement that we do not plan on stopping support of GR3 really until we're at that point where the community has already moved over to 4.0. So GR3 is going to live on. If you've built stuff on GR3, there's a very active ecosystem. You know, really until no one feels like maintaining it anymore, that is GNU Radio for the time being. So I know that has been a point of concern for various people in the community, that you know, the new shiny thing, squirrel, we're going to run after GR4, but that is not the case. So back to this, I really think that you know, what it's going to take here back in this visual is, you know, we need an elevator here for these folks. We have to build the tools to make it easy to get from where we're at GR3 to GR4, and then also the tools for people to get that are not using GNU Radio onto GR4, and then that becomes GNU Radio. Oh, more. So that's really all I had to say on that, and I want to open up a Q&A session here. Make this a bit more interactive. Sorry, I've been talking at you guys for an hour now, but make this a bit more interactive. I would be remiss if I did not mention GRCon 24, which is happening in a few weeks. If you're interested, or you know any of your colleagues might be interested, just gnuradio.org/grcon24. All the info's there. And yeah, we of course we can use your help a lot of different ways. GNUradio.org is the place to go for more information, and thank you.
So now the session is open for questions and answers. If anyone has any questions related to what has been presented, or questions about GNU Radio in general, its future, you can ask right now.
And I don't have to be the one to answer the questions. You know, there
are many.
We have you know, Marcus, Ralph, anybody. This can be open discussion. Would be excellent.
Maybe to spice up a little thing, I'll ask the first question. So do you have any ideas on how long there's going to be the superposition between GNU Radio 3.10 and then 4? And is there going to be any evolution of the 3.10 from this point on, and how long?
Yeah, so there's still more things that we want to add to 3.2. You know, if you put 4.0 aside for the moment, you know, that I think I had a slide back there about various things that we want to add to 3.10. We want to continue to make GRC better based on Qt. We want to add support for SIGINT, and things will come along. Various people have you know, different requirements, things they want to add into it, and that's, you know, it does continue to be an actively maintained project, and that's not going to stop. In terms of of how long that goes on really depends on at what point 4.0 becomes something that resembles the same usability as GR3. So we want to continue to push on GR4 and find partners that can help us, make that look more like, bring in GRC into it and all of those aspects. But yeah, we expect those to live in parallel for some time.
Okay. Any other question?
Could you go back to the slide where you said for a GNU Radio 4.0 official release we need the
Yes,
things?
yes.
Yeah. So what do you think is like the main? What is the thing that the community needs to invest most? Because I guess this part of this is also that, as you said, we want to transition this from a very dedicated development effort by GSI and FAIR into something that is a community project. So at some point we need, to get the community to do stuff. What is the thing where you think we could start people on right now?
That's a good question. I think right now, there's a bit of a chicken and egg problem. I think the most value right now is taking it, using it, building an application with it, and then that's going to be an iterative process, and then that's going to take us back into the core and say, oh, to do this application, we might need a little bit different scheduling or something like that. So I think the most valuable thing is using what's there, building something on it, not building your entire workflow around it, but really prototyping something on top of it that could be usable for you, learning more about it, and feeding that information back to make the core better and to start to build up an ecosystem of applications built on GR4. I don't know, what's your thought there, Marcus, as far as?
Yeah, I honestly ask that because I have very little clue about that. So the Python integration is something that I feel is very important to a lot of, for getting things rolling, right? And even if it's just in terms of getting like the small bugs out by, letting enough users hammer the software until it breaks. Mm-hmm. But I feel that if I start adding like some Python bindings right now, it might not be very clever because things are in the flow, right? This is still fine. But me now defining an API by putting a Python thing on there might not be clever. So that's where I came from there.
And Python bindings are a good point because that does make it accessible to a lot more people. If we can configure flow graphs and build up a set of blocks and have them wrapped in Python, a lot more people are willing to do that necessarily than do ground up C++ application and work with compilers and stuff. So, yeah, Johannes. Come down here. Oh.
All right. So there's this one bullet point equivalent block set, and I think that's always a moving target, right?
Which bullet? Which bullet
the
point?
equivalent block set. Yeah. So okay. Sorry. Okay. So there's this bullet point equivalent block set, and I think that's a moving target. So that might be like this one thing that will not be on par for years, and even if it's at one point, by the time people realize it, it's not anymore. So it might be better to put it around like a basic set
Right, right.
And
Yeah, equivalent is probably
there's
not the best word
probably
there.
blocks in radio at the moment that, well, it's a good opportunity to deprecate them.
Yeah.
So there's lots to be had there. And the other thing that came to my mind is that if we have Python bindings, like for GR4, it might be really nice if we could just use them directly from Python, like the actual block function. You know, that might make it easier for people to use GNU Radio functions under the hood and then integrate that into FlowGraph whenever they need it. So that's like an easier transition from experimenting and figuring out like what do I really want to, oh, now I use a GNU Radio FlowGraph. But that's just a thought. Thank you.
Yeah, so I think that, yeah, that's probably bad wording on equivalent block set. I think maybe a better way to phrase that is enough blocks to do interesting things. But yeah.
Yeah, this is Ralph. Hi. Thank you very much for your talk and for the insights, also like for the high-level meta aspects, which are, I think, for as much as this project is about technology, it's also about people and community. And I find it always interesting, depending on where you look from. Let's say you look from the low level, you say, obviously, the most important thing is performance, and then you start building your way up, Python bindings, and maybe eventually graphical user interface, because if you're building C++, why do you need a UI? You have everything in code. What I discovered, what the diversity GNU Radio community is huge. We estimated at some point of time at least 10,000 users. And most of the users, even though I'm a developer and a user, it's like most people, the entry level for seeing GNU Radio, especially this flow graph concept, is via visual. So I think the most important thing, from my view, would be the GRC integration, to have a bridge. I mean, like, because that gives people an idea to tinker around with that and see like, oh, is it worthwhile or not? And once they see it's worthwhile, it's interesting, you have good, nice visuals, you can sell this also to your supervisor or your organization, then you can say like, oh, we want to do an extension. And I think then the next step is how do you write out-of-tree modules. And for Python bindings, I mean, like we prepared the code base that it's easily wrappable with Python. We made also some proof of concept, but I think there's some technical question because it's also like, how far do you move with the standards? Do you stick, meaning the GR3 code base is done largely with PyBind 11, which works, but it's a bit dated and nobody is maintaining this. So the question is like, do you go with PyBind 11, NanoBind, or do you say a new approach is PyPy, where basically the developer says like, just wrap what is needed on the fly, and you can also generate faster bindings. The thing about the blocks, I'm less worried. We have like an issue tracker, like let's say an epic, which we put in the project, where we listed, I think Simon made a tremendous effort of listing all the blocks that are implemented in the core library of GR3. And most of the things that we needed from, let's say, from a GSI fair perspective, we said like, okay, we have to anyway tackle it, and we implemented it. Some of the blocks we left open because we thought this is a good entry point for others to chip in and say like, oh, this is an easy enough block. GSI fair forgot it. Yes, we forgot it on purpose. So that let's say all the low-hanging fruits are not all gone, and then we say like, okay, now you can do the most complex thing, which is writing your own scheduler, but to have also like an accessible entry level. So I think the most important window to GNU Radio is probably the UI. Mm-hmm. We have an in-house UI which serves our own purpose, but we can't. People can copy, share this code, but we can't commit on developing a UI that is suitable for this vast, diverse community. And I think this has to come from the community. Somebody else who has a inclination for UX and UI design. So UI. And last but not least, this was like some of our attendees also mentioned. After that, once you get into the out-of-tree development, you need people who are educators, communicators, good technical writers. Because I mean, like, we have now at GSI Fair like a group where we just need to phrase like 1 or 2 words, and then we can read each other's minds. So we have a very high cohesion, and that works very well. But we realized that this came at a price of that we that you have to translate this also to other people who are new to the project, who have never worked with C++, never worked with this modern paradigms in programming. And I think there it's useful to have a fresh perspective from outside, so like, okay, I understand now what it's doing, and if you communicate it this way, it's easier for others without having to have first a double degree, double PhD in C++ and signal processing before you can use it. So having educators, communicators, so lots of non-software development work we should entice and get people on board.
Yeah.
As a follow-up to what Ralph just said between GRC and Python, I wonder if Python is the default output of GRC, and to the best of my knowledge, C++ generation was added later and is not fully supported, or there are blocks that will not properly generate C++. And I wonder in terms of order whether having native C++ generation out of GRC for GNU Radio 4 would not make more sense, because if users are, as Ralph just said, using the graphical interface to generate a GNU Radio flowchart, then whether it's Python or C++, they don't care. They just see a flowchart running, and then maybe adding Python. But yeah, I agree that GRC, GNU Radio Companion, generating something that the user can execute, whether it's C++ or Python, would maybe be the most urgent tool to get people addicted to GR4.
Yeah, no, I mean, even in GR3, being able to generate C++ only flow graphs out of GRC is, highly desirable. 4.0, I think there's some compile time issues that might not quite be as seamless. Or I guess GRC would generate the code, but one that I was going to go back to something that could help here. So the GSOC project that I mentioned here, where GRC has become more modular and workflow based. So this could really enable something like that, where rather than changing much about GRC in order to output, say, a GR4 flow graph, it might just be a workflow that gets defined. So that might make things a little bit easier there. And then as the Python bindings are developed, then that's just another workflow. Here's how you render a flow graph with the GR4 Python bindings.
Kind of just following on this, I think there's, except for this part where now GRC has more standalone applications in it in the pluggable workflow, that I think it's, this is a result of many conversations last night. Yay, I enjoyed all those about where is it headed, how do we get there? Because there is a part, if we realize that the user interface, whatever, like GRC, prime, or whatever it is that I don't know that, I think Python is not necessarily not required.
No.
Is first order business. If you've got like some graphical interface and it works and it's interactive enough where that's some threshold of I make a change and rearrange it, and there's some like number that was kind of, numbers were talked about, like how long will you wait till you're happy, and it's a relatively small number, it's not like 5 minutes, it's more like 30 seconds than that. And then, maybe there is Python, maybe. It
doesn't have to.
I'm not saying that there shouldn't be, but if we look at keep our priorities straight about how do we get people happy, let's not presuppose that we know the inner layer effectively.
Right. Yeah, and the priority is having a solid core, and I think the work that Ralph did here to make it able to do those dynamic connections is very critical for GR4 code base to be able to work in something like GRC.
Maybe you can comment, actually, this development was done by Ivan. He wrote the plugin system and also make it possible that you can define and generate runtime flow graphs. So there is not a need that if you build an application on top, as you mentioned, it doesn't have to be Python. It can be also C, C++, or any other thing that can talk to the SO. And then you can also load your own SOs. And we try to keep, until now, a very strong compatibility with the GRC YAML format. So we write the same YAML format that GRC does and also read the same YAML format. The only difference is that the naming of the blocks presently for GR4 and the string naming is different. So for all the UI builders out there, in theory we have already a reader-writer for this YAML format, and maybe we just need a translator for, okay, what was called add_ff block is now called add bracket float block. So I think we're ready. I feel that we're ready for having also production-grade UI built on top of that. So the API is there. But the question is like, which path? Is it a mandatory path via Python, or via directly that you embed it directly from Qt? But we need people for that because there's lots of stuff that is not related to the low-level thing.
In the slides, there's a lot of mentioning of 3.x. Does that mean there's like a requirement or an idea about 3.11, or is everything you do not a breaking change to 3.10?
So what would trigger us going to 3.11? It would be either a major API change or some major feature change, but I don't think that, maybe Marcus, you could comment a bit more on this. There's no specific plans, but.
Yeah, so bit history there. So Jeff Long has been the release manager for the 3.10, 3.9 branches, delayed 3.8 branch basically. And he very understandably said, okay, this is already too many branches that we're maintaining and we need to have like a life cycle expectation for that. And if we're going to maintain GNU 3 in parallel to ramping up GNU 4, we might need to, limit the changes that we do on one end so we can both have the developer force on the other, as well as not breaking people's expectations on the thing that is supposed to be stable, right? So in the current state, we're not trying to not do a 3.11 release. That's basically, we're trying to not break things again. On the other hand, I don't think that is a hard rule. We don't want to end up in a situation where we were with GNU 3.7, where it's like 5 years, the same version, and things really get stuck, right? It's just that we're a bit more careful about whether we need to do a new version now than we were going from 3.9 to 3.10, which was a very smooth transition anyways. So the situation here is we don't have an acute need for 3.11, so we don't, right? If there is something like we find a bug and it breaks people's applications and we need to fix that, but it will break API, then of course there will be a 3.11. But either way, whether it's going to be 3.11.14 in 4 years of time or 3.10.25, it will probably still be maintained in some capacity. But this ties into something that you kind of skipped over very quickly in the end. Jeff is kind of retiring. So we need an equally good team, honestly, of release managers. And anyone who does that gets, kind of a bit of a freedom to do as they, it seems feasible to them. And so if you're in the business of making long-term plans on GNU Radio 3.10, 11-ish, right? Do get in contact. I mean, you're working for a larger agency. Maybe this is actually something where it pays back pretty well to invest a bit of time regularly, have someone do a bit of contribution on the maintenance side, and then get control over aligning release schedules with other things. Like Josh mentioned that it was very important to align the 3.10.9 release with the Ubuntu 24 release, right? This is something we have in mind. So I was like, when is the next very granular release of things where we really want to get into, and then we aim for that, right? This is actually work that needs to be done, but there's no reason that this maintenance work cannot also align with other goals, and people can cooperate on that. So this is really a call to anyone. If you want to maintain, get in touch. We're trying out different things to do that, like dividing, like you're caring about this GRSA audio submodule very much because you're doing a lot of audio with GNU Radio, and you just want to care about that. By all means, you can be the audio guy and just help decide what goes in there or not. Just get in touch. We need to divide this job a bit more into more shoulders because it's not good if someone retires and then there's not a team to pick someone else from. Yeah.
So should I put your name down?
There's no immediate feature that needs like an API update for 3.11. So.
I mean, what necessitated 3.10, like 3.9 and 3.10 were very close. It was that custom buffers feature that necessitated that.
I have a question. So we're all talking about, the transition from 3.10 to 4. I remember when I was using 3.6 at some point, we changed the make system. And it broke lots of out of 3 blocks for the ones who were starting on 3.7. I'm not sure if it was from 3.6 to 3.7 or even before. But I remember there was like a how-to on how to convert. So there was a step-by-step instruction on how to do that. I wonder if there's something like this already for 4. It could help people start transitioning some blocks and testing them out.
Yeah, no, that's something that we absolutely will need as we start rolling this out as to pushing people in that direction. But yeah, we're not at that point yet. And the work that Danny's doing is a big part of that. It's like how do you actually build a functional application with GR4? Just having that documented is a key component to this.
But even just the out of 3 blocks, I mean, it would be interesting to have how-to, someone who has actually took something from the 3.10, then ported it fully to the 3.4 and documented the whole process.
Right.
Then write a little document that explains how to do that.
May I remind you that is actually the reason of this workshop. So what we told yesterday, we closed all the doors, and then everybody is writing a blog, some piece of documentation, and once this is done, we open the doors again. That's also the reason why we have like some coffee and drinks here, so that you're all supplied and don't have to run away. And then if you have the smoke, like when you vote for the Pope, white and black, everything is fine. But the idea is like to get people into giving an introduction, what is GNU Radio 4, and then let them tinker. And we have like several people in the afternoon session that will help you answer questions. And then the hope is that people who use it will document it in the way how they understood it. Because if I understood it, it's nice. Obviously, one always understands oneself the best. But it's important to have this feedback also for us. What do they think is important what we did? Maybe we spend some resources on time, effort on things that are completely irrelevant or roadblocks. We had some concerns with, can we do this decision because there might be some unknown user to us that says like, oh, if this is not working, it's a deal breaker for GNU Radio 4. For example, packet radios. And that's, I'm thankful for Daniel that who explored it from a different angle because we're, at GSIFA, we're not telecommunication experts. We know our signal processing stuff, but we don't know everything about satellite communication, secure comm, and so on. And this is supposed to be a dialogue to get to know each other and to see what is relevant at the core and where we have to branch out, and then to develop this and continue on this.
Yes, I just want to remind everyone that there's going to be the presentation of Daniel in the afternoon. I think it's going to be really interesting because it's going to... Oh, in the morning, sorry. In the morning after the coffee break. I'm sorry about that. And we will see exactly how he has done it. So I think this is going to be really interesting. And I'm not sure. I think we will just go directly to the coffee break. It's 10:30. If you have any more questions, you can ask Josh directly. So thank you.
Un, deux, un, deux.
Okay. While the last of you get seated, I'm going to briefly introduce the next section of presentations. So this is the contributed presentations. First one is by Jean-Michel Fried, who's already here on the podium, and he's been working a lot with clocks synchronization at the University of Besançon, at the lab called FemtoST. He's also, as I said previously, one of the organizers of the GNU Radio European Days. And yeah, you can go ahead, take it away.
Thanks, Leo. So I wanted to talk to you about using GNU Radio for radar applications. Now, one reason why I wanted to share with you this insight during this conference is that last March, I believe, we were at CERN at a White Rabbit workshop. I'll talk about White Rabbit. And usually when I do my passive radar measurement, I have X310s, so Etudes Research X310 software-defined radio platforms, dual channel, and I'm using the White Rabbit network for synchronizing. So White Rabbit is a system developed by high energy particle physics laboratories, including CERN, including GSI, for synchronizing these software-defined radios. And as most often during these conferences, the guys at GSI, including Dietrich Beck, were presenting the development in GSI about White Rabbit. And when I realized that the conference, GNU Radio conference, would be held in GSI, I had to put these two together. So the team of White Rabbit developers of GSI were kind enough to send me a few of their boards. These are all GSI boards. And what I'm going to show you is how we can synchronize software-defined radio receivers for coherent measurements using the White Rabbit boards, PCI Express boards dedicated as developed by GSI. And of course, here I want to highlight the unique opportunity at GSI of having the developers of GNU Radio 4, of having the developers of White Rabbit in the same location. So I hope you can find some way of merging these two activities. So radar, usually radio frequency detection and ranging, is considered as a way of measuring the distance to a target. And it's common to say the range resolution is the speed of light divided by the bandwidth of the signal, divided by 2 because it's a two-way trip. And the problem with this broadband radar, where you want to maximize the bandwidth in order to have as high a range resolution as possible, is that if you increase the bandwidth, you also increase the noise that you integrate in your measurement. And if you integrate more noise, well, your signal-to-noise ratio is degraded. So an alternative to this is to consider narrowband radar. So if you have a narrowband radar, the problem is the bandwidth goes to 0, and that means that you might not have any range resolution. One application of this narrowband radar is interferometric measurement. You want to do just a phase measurement, so you don't care about the absolute position, but you just want to detect the displacement at the expense of half wavelength uncertainty, because you have two-way time of flight. Another application is that the laboratory I come from, which is time and frequency, so our activity is to have high ultra-stable clocks, ultra-stable oscillators, so the ability to timestamp events with high accuracy meaning sub 100 picosecond, and high stability clocks. And one activity here is to use these high stability clocks for detecting fine frequency shifts. And what are the frequency shifts that we're interested in is moving target. If a target is moving, then you have Doppler shift. And if you can have a fine Doppler shift measurement, you have a high velocity measurement, high accuracy velocity. Now, from the laboratory I'm located in, 40 kilometers away, there is the Space Surveillance Radar Emitter in France. We have the GRAV, Grand Radar Adapté à la Veille Spatiale, which is a military radar. To the best of my knowledge, is 400 kilowatt transmitted at 143 megahertz from 40 kilometers from the lab. And it's a bistatic radar with a receiver south of France in the former missile silos, Plateau d'Albion. And this bistatic radar requires high stability in order to compare the Doppler shift introduced by any flying object, any object flying over the metropolitan French territory, including spy satellites. So, of course, this system is used to detect whatever is flying over the territory. So what I'm interested in is, I'm located over here, the GRAV radar is over here, and in illuminating anything that is flying over our territory, including planes. And if we don't have any range resolution for a satellite, all you want is to detect Kepler parameters. So from a few velocity measurements, you get all the parameters of a satellite orbit because they follow the third Kepler law. In our case, we would like to have locations of planes, and if you want to have location of planes without range information, you need to do direction of arrival or time of flight measurement. So multistatic radar is a very well-known topic. This is a NATO textbook about multistatic radar. So it's a field that is pretty well-known, but just so that you can follow the discussion, I have to remind you, if I have a multitude of antenna to get azimuth information or azimuth and elevation information, then if you assume that a plane wave is reaching this array of antennas, then you introduce a phase shift which is related to the angle of arrival and the distance between the antennas with respect to the wavelength. And in the classical case of a uniform linear array, the ULA, then this phase shift is a constant between each antenna. Now, if you have something with a phase at the nth antenna, which is n times delta phi, well, if you think of what is a sine wave is a constant increment of a phase as you have constant sampling in time domain. So what you have here is exactly the same thing as a sine wave. If you want to know what is the frequency of a sine wave, you take the inverse Fourier transform. Exactly the same story here. If you take your measurement of a phase along the various antennas and you want to know the direction of arrival, it's an inverse Fourier transform in the space domain, not in the time domain. So what is the actual measurement? A multistatic radar measurement is collecting a matrix where you have n antennas, each collecting p samples, time domain. And if you want to do migration from antenna position and time towards direction of arrival and frequency, then you take a 2D Fourier transform. So this is why whenever you look at SAR or synthetic aperture radar or multistatic radar, you will see inverse Fourier transforms. And this assumes that over the integration time, your environment is static. So if you take Fourier transform, you assume that your direction of arrival is a constant. So if you have a periodic sampling of a sine wave and you take the inverse Fourier transform, and since Gauss, we know that there is an efficient way of using the symmetries of trigonometric functions, which is called the fast Fourier transform. If you take the IFFT of a sine wave sampled periodically, you get a Dirac function. And this is known to be an n log n complexity algorithm. However, the assumption here is that you've collected each and every sample periodically. If you think of this in terms of antennas, it means I need to have as many antennas as the red dots in the space domain. I need to buy a lot of X310s. And the last time I checked, X310s are 10K euro. That's going to be a very expensive radar. Now, another expression of this is you can express a Fourier transform not using the symmetries of the FFT, but going back to basics. You're multiplying your samples with a matrix where you have the time over this direction, incrementing at a fixed frequency, Fourier frequency. And on the x-axis, along the columns here, you have frequency 1, frequency 2, frequency 3. And you can express a Fourier transform as a matrix multiplication. Now, if you keep the bijective properties of a matrix, it's a square matrix. You have as many times as you have frequencies, and it gives you exactly the same frequency. I offset so that you can see the difference between the two curves, but whether you're taking IFFT from MATLAB or you're taking the matrix multiplication, you get the exact same result. Why is this a useful information? Because no one said you needed to match the properties of a Fourier transform, that there's as many frequencies and times, and no one said that the time has to be regular or that the frequencies have to be evenly spaced. You can say, I'm going to have randomly timestamp data. What's important is you need the timestamp. You cannot say, I randomly sample data. If you know at which time you sample the data, no one said you needed to have all the red dots. Okay? So let's say that, for example, I only collected a few of these samples. So I keep all the output frequencies as before, but now I have fewer points, fewer samples. Of course, you all know that if you gate, the Fourier transform of a gate is a sinc function. So by having fewer samples, you have, well, the spreading with the side lobes due to the sinc function. But now we have a rectangular matrix. We have many more times than we have many more frequencies than we have times. We can do this a bit further by saying, well, maybe I only have a couple of samples over here and a couple of samples over here. What's very important here is don't tell anyone that I'm not meeting Shannon's criterion. Of course, these two samples are nearby, and this is why I still have high equivalent sampling frequency. However, I'm creating artifacts because these samples here are now separated by widely unknown quantities. So you spread the sinc function, but still you can operate this calculation. And now you see I can have information about the inverse Fourier transform with only 4 samples. 4 samples in the time domain. Remember, this is 4 antennas in the space domain. So now we have an expression in the matrix domain where I have all the frequencies, and the dual quantity in our analysis is the direction of arrival for very few antennas with the disadvantage of the side lobes. And now if you say these 2 antennas are further apart, which is what you do with VLBI, you say I have 2 antennas which are not nearby but now further apart. Well, you've got these comb of functions here, which are now you've got the high resolution of the far away VLBI antennas, but because they are far away with missing dots, well, you've got the envelope. And this envelope, what is the envelope? Of course, if I just were to take 1 antenna here and 1 antenna here, you've got aliasing, you lost the high sampling frequency of the 2 nearby antennas. So now that I went quickly through the mathematical basics, why is this useful? Well, what your colleagues at GSI here, Dietrich Beck and his group, lent me is this White Rabbit board. Why do I need this? Because I'm going to have widely spaced apart antennas, and I want them to be phase synchronized if I want to have direction of arrival. Now, typically, it's considered that White Rabbit will give you something out of the shelf of in the 50, 60 picosecond time resolution. So it means White Rabbit will send a signal out of a source. It happens that the lab I come from is dedicated to high stability frequency, so we have access to free hydrogen maser, we have access to cesium clocks compared to the Paris primary reference. So this is my master clock. My master clock goes to a White Rabbit switch. My master clock is located over here. So the 1X310 receiver, which is an antenna located over here, is 50 meters away. Now remember, light is propagating 300 meters per microsecond in air, 200 meters per microsecond in an optical fiber. So 200 meters per microsecond, if I go 50 meters here, I already wasted 250 nanoseconds. And I said White Rabbit gives you 60 picosecond resolution. Well, what happens is that White Rabbit is measuring the time of flight and compensating for the time of flight. So this is my first antenna array, 1X310, 2 antennas located over here. And then we have the Besançon Observatory located over here, 600 meters away. 600 meters is 3 microseconds in an optical fiber. But again, White Rabbit is compensating for the time of flight. And we have our high accuracy timing capability at the Besançon Observatory. And this is my teaching class at university, where I have also access to the roof, so I can put another set of antennas 600 meters away. So you see that we can create, using White Rabbit, an array of antennas, 2 antennas over here, 2 antennas over here, each fitted with 1 X310 dual channel input, and we can try to do some measurement. These are the outputs of the GSI PCI board, which are running White Rabbit core, and you see that, well, they're locked, good. And you see here that the phase tracking is enabled, meaning that the White Rabbit are indeed getting the right signal. And here you see we have something, if you remove this is picosecond, so this is 820 nanosecond. 820 nanosecond is the time of flight from this location of a miser here to here. And here you have 650 picoseconds, and here you have 10 microseconds. 10 microseconds is, if you remember, 200 meters per microsecond. That's about 5 kilometers. If you don't have straight line over here, well, that's the path followed by the optical fiber two-way trip. So you see here I did the calculation for you. So you see here we have our 2 White Rabbit boards, which are clocking the X310s, and indeed we do have phase synchronization on all the X310s. So what can we do with this? Now, just be a bit careful, and this is not a negative comment with respect to the GSI work. I should emphasize the GSI boards are amazing for what they're doing. I just want to warn you that I really want to have something that is hardware agnostic or vendor agnostic, and even though CERN and GSI are using the same White Rabbit core firmware, well, when the first time I ran this, these are the 1 pulse per second from the CERN White Rabbit switches. These are 1 pulse per second from the GSI board. They're aligned to better than 1 nanosecond, so they're doing the job the way they want. However, you see that this is one hardware, this is another hardware, and there is a time offset between the two. So I just warn you, be careful that when you're using the same gateware on an FPGA running on different hardware, well, you introduce, we're talking here about nanoseconds, and one nanosecond is 20 centimeters on a PCB. So be careful that there are some latencies that are introduced, unwanted latencies, and the GSI people told me, yeah, we know we have to repair this, but just be aware that you have to be a bit careful about the impact of running the same firmware on different hardware. So having said this, in which context can I use this? So Grav Radar is broadcasting at 143 megahertz. You might know, if you're a ham radio, that sometimes people compare their clocks or their oscillators to the Grav reference signal. Now, Grav is broadcasting a signal at 143 megahertz, and the X310 is sampling at 200 megasample per second, which is Nyquist frequency of 100 megahertz. So if I want to record the 143 megahertz, I'm actually going to use on purpose the second Nyquist zone. So it's aliased signal. And the Doppler shift, when you're doing radar measurement, you have to remember that the signal is going two-way. It's going towards the target and coming back from the target. So the frequency offset is actually 2 times the carrier frequency times the velocity divided by speed of light. And it happens that because the velocity is about 150 megahertz, the frequency is 150 megahertz, 2 times 150 is 300, divided by 300, it happens that the frequency offset of Grav is about the velocity of a target in meter per second. So if you think of subsonic aircraft, so sub 330 meter per second flying aircraft, well, you expect a Doppler shift about in the 300 hertz range. So you're sampling your megahertz signal, and then you need to decimate until you reach a few kilosamples per second. And one nice thing with White Rabbit, it's a gigabit Ethernet switch, meaning that you can also broadcast the data over the fibers of White Rabbit. I don't need to go through all the firewalls that you've seen. I have to go through the Besançon Observatory. I have to go to university. The nice thing with the White Rabbit switch is a gigabit Ethernet. I have a few kilosamples per second. I just run my stream of data over the White Rabbit network. If you do a quick calculation, 60 picosecond standard deviation of phase synchronization at 143 megahertz gives you something like 3 degrees of phase stability between the various receivers. So this is what the GNU Radio flowchart looks like. Be careful that if you want to synchronize multiple USRPs, you need to run a multi-USRP source, because the computer running the multi-USRP source is going to broadcast the signal to all the USRPs to synchronize them. You see that the center frequency is 56.95 because I'm using the second Nyquist zone. And as we all know, because if you want to decimate by as much as, you see here 25 divided, so that's 125, 1,000. So if you want to decimate by 1,000, either you put one filter with a huge number of taps, or you cascade and decimate. And this is what I'm doing here. I'm cascading and decimating my low-pass filters until, from the few 100 kilosamples per second I collect initially, I end up having something like 640 hertz baseband. So now that we have all this data, here is a typical measurement. These are 3 of the 4 antennas I put on the roof. And because you're only 40 kilometers from a 400 kilowatt radar, you just put a monopole on the roof, and that's enough to get the signal. Now, you will have here all the tracks. These are waterfall plots, sorry. So this is the frequency, this is the time. And as I told you, the frequency happens in the Grav radar to be equal to the velocity in meter per second. And you have here the time, you have frequency, and these arctangent functions are actually the projection of the straight flying plane on the baseline between the emitter and receiver. When you've got this kind of kinks over here, this means that actually the plane has turned and the projection has changed. And when you've got this big blob here, this is a fighter jet, because fighter jets, they don't fly straight, they just keep on moving in all directions. And so your Fourier transform doesn't integrate in one nice peak in the frequency domain, but you've got a whole range of velocities. And this actually is a direct wave, direct from grav emitter to our receiver. And this is a beautiful straight line because we're locked on the hydrogen maser. If you were to run this on a standard TCXO, on a temperature-controlled crystal oscillator, you would see this line drifting in all direction because you have intrinsic local oscillator motion. And so this beautiful straight line, which allow fine Doppler shift measurement, are thanks to the high stability local clock. So if you want to know why we're being paid for making high stability local clocks, high accuracy Doppler shift is one reason. If you don't have a fighter jet, this is the kind of peaks that you get. Each one of these is a plane flying towards our receiver. So if you do this over time, you've got time domain over here, you've got the three of 4 antennas, and each one of these is a plane coming towards us, crossing the baseline, so 0 Doppler shift, and then going away from us. This is super simple octave script for just taking short-term Fourier transform. But what's amazing, this is just incoherent, this is just magnitude, as we've seen with the optical fiber presentation yesterday. But because now we're coherent, we can actually do phase measurement. And if you take the phase difference with respect to the first antenna, this is 2 - 1, 3 - 1, 4 - 1, you've got these beautiful curves that start here at -3 radian, that move slowly towards +3 radian, and then you've got phase wrapping. So you see that we can expect to have a beautiful direction of arrival measurement, and this is just angle of the IQ stream, second antenna divided by first antenna, so phase subtraction. So now that we have these beautiful, continuously varying phases, what can we do with it? The first thing is we might want to have azimuth elevation. So in this example, I didn't put my 4 antennas far away. I put them just co-located on the roof of our university. So you have here a square 1, 2, 3, and 4 antennas separated by 46 centimeters, that's quarter wavelength. And if you think of it, you have a plane coming towards your square baseline. You just do some quick projection. You've got theta the elevation, phi the azimuth, and you say that you've got the x, y, z baseline, z equals 0 because they're all on the same plane. So you can very easily calculate that from your phase measurement between the 4 antennas, you end up having azimuth and elevation. So we've got here azimuth and elevation, we've got azimuth as estimated by 2 of these antennas, we've got elevation as measured by 2 of these antennas, and then you can end up plotting for the whole time what is the evolution, so the velocity as a Fourier frequency, azimuth and elevation. Now this is such a crowded chart because there are so many planes flying over our university, there's nothing you can see with it. Except during the night. During the night, there's few enough planes that you can separate the individual contribution. And if we zoom in, well, that's the kind of velocity fluctuation, that's our azimuth information, and that's our elevation. That basically gives you an insight about the path, the track that is being followed by the plane. So that's a 2D information, but it's not benefiting from the fact that we have multi-antenna. Now we're using the square baseline pattern, and this gives us a 2D position of a plane. Now, if we go back to the initial insight of saying we have a uniform linear array, possibly with a gap, when we do the same story as we did before, we take the inverse Fourier transform. And again, this is another 24-hour measurement with the antennas this time aligned on the roof. And you can do the same story, except that now you only have azimuth. You don't have elevation anymore because all the antennas are aligned. And again, we have overnight the gap. And we can look at what is the evolution of the angle of arrival and the frequency offset. So you've got continuous lines that hint at a properly measured angle of arrival from array using direction of arrival. And as I told you, if you spread further the antennas, if you spread them further away, so now I put 2 antennas 50 centimeters from each other and now separated by 7.5 meters, as you can see here, we've got the frequency shifts of the velocity, and you have here the result. And you remember, as I told you earlier, if you've got these 2 samples far away, you've got a comb of sharp peaks, and this is actually your comb. So here you have one of the direction of arrival estimates, except that this is over an envelope, and this envelope you have to do some feature tracking to only follow one track and not the other one. So that's exactly why we have these lines parallel, because one of them is the path of a plane, but we have uncertainty because of two faraway antennas. Finally, I told you that quite a few people, ham radio, are using Grav radar as a frequency reference, and I was wondering whether I could use Grav radar for frequency dissemination. Now, what makes this slightly difficult, if you look on the internet, you'll find some document that says that Grav radar is actually sweeping a beam, and because you're sweeping the beam, it's an electronic phase array. The problem with electronic phase array is each beam is phase coherent, but from one beam to another, you don't really know what's happening. The electronics is introducing phase. So if you zoom into a time domain evolution of a phase of the signal that we received, this time we're not looking at the planes, but we're looking at the direct wave from Grav to the receiver. You see that actually you see the sweeping of a beam. This is beam number 1, number 2, number 3, number 4, number 5, number 6, and then it repeats again. So actually you have 8 beams, and you need to select out of the phase one beam, and then you measure the phase stability or the oscillator stability of the oscillator clocking Grav, and you try to detect what is the stability. If you do this analysis, I'm not going to get into the details, what makes it a bit tricky is that you get a wrapped phase. Even though we have hydrogen maser, well, your phases are always drifting one respect to the other. And this is an unwrapped phase. And if you look at the Allan deviation, so Allan deviation is how much does the phase fluctuate as a function of integration duration. So on the x-axis, you've got the duration of a sliding average. On the y-axis, you've got the relative stability. And you see that Grav radar time transfer gives you something at about a few 10 to the minus 11 at 10 seconds, decaying as a square root of tau integration duration. And my colleague Claudio Calosso from the National Italian Institute tells me that 1 over square root of tau is typical of a link-limited stability, meaning that we're not measuring actually the Grav stability, but we're measuring all the noise and all the uncertainties of a broadcast signal between the emitter and our receiver in Besançon Receiver Laboratory. Just to give you an insight, this is the Allan deviation of a hydrogen maser at 10 to the minus 13. So what we're measuring is not our local hydrogen maser, but it's definitely the Grav link. Our hydrogen maser is more in 3 orders of magnitude, more stable than what we're measuring here. So as a conclusion to this presentation, I wanted to show you how GSI has this unique opportunity of having in the same location White Rabbit and GNU Radio. I'm giving you this example because I don't have an accelerator at home on radar measurements, but I think that merging time synchronization using White Rabbit and software-defined radio opens a whole field of opportunities. Now you could, White Rabbit has been now standardized as PTP high availability, but it's becoming more and more widespread thanks to this. I wanted to try to show you how this measurement can be applied to 1D or 2D analysis, and actually how you can do time transfer using this system. Now, White Rabbit at the moment is only used as one part White Rabbit generating 1 PPS and 10 megahertz. On the other hand, the X310 receiving 1 PPS and 10 megahertz, which is fine for an X310, which is actually used for receiving anything. But what if you want to have something other than 10 megahertz? And part of my work is to try to see how I can generate any random frequency. There is one chip from Analog Device, which is called a network clock synchronization chip, that will generate anything between 0 and 400 megahertz locked on the 1 PPS and 10 megahertz. And one beautiful development at CERN, at least I'm aware of what they're doing at CERN, is called this RF over White Rabbit, where instead of having peripherals clocked by the White Rabbit signals, they actually integrate they integrate the radio frequency, DDS, or numerically controlled oscillator inside the same FPGA receiving the White Rabbit clock, meaning that actually you put in the same FPGA all the capability of time synchronization and radio frequency acquisition or generation. And my vision here would be to have the White Rabbit core as one of the plugins or ideally for RF NOC, but that's maybe too much to ask. On a general purpose FPGA, here, these FPGA, the only drawback is that they need 2 external programmable oscillators, and the vision is modern FPGA have find enough PLL that you can get rid of these external oscillators, and that means that any FPGA fitted SDR should be able to run White Rabbit synchronization. So that would be the perspective of this work, and for FPGA specialists, fine development if you're interested. And with this, I thank you for your attention.
He just finished at the right microsecond that his lot is finished. This is impressive. So unfortunately, we don't have any time for questions, but you can always catch up with Jean-Michel during the lunch break. So I would just like to invite Daniel. So next presentation is by Daniel. Many of you already know him. He's a very active developer and tinkerer of radio. We see his developments all over the place, all over the internet. And well, he's mainly working as a contractor, right, with satellites? Satellite communications. And your alarms. And I think, yeah.
To shift it? Yeah. Okay, perfect. So the work I'm going to present is called GR4 Packet Modem. I guess this is an out-of-tree module for GNU Radio 4. It's probably the first out-of-tree module. This is a packet-based QPSK modem, although you could do other modulations as well. It was implemented from scratch in GNU Radio 4.0. This is a project funded by GNU Radio using money from an ARDC grant, as you saw. And the project has been running from May to September, so it's almost finished, but there's still time to do more stuff in September. There were 2 main goals for this project. One is to test how GNU Radio 4.0 currently works in a digital communications application, because as Eric was saying, it will surely work great for FAIR, but we also want it to work great for all the SDR community. So one goal is to test how this works and to give feedback to the FAIR team about what things work well, what other things can be improved. And the other point is about documentation. I'm easing the way for people to start coding into GNU Radio 4.0. So if you have a set of blocks and if you have a complete application which does something useful, you can use the blocks as examples to do some similar blocks. You can use this application to customize it. So that's the main deal here. When I began this project, the design goals or criteria I set to myself were the following ones. So I wanted to do a modular implementation with many small blocks. This is also the way I work in GR3. And for this project, I think that was really important because, first of all, if you want this to be usable by other people as examples or components of their applications and flow graph, you need this 1 block per functionality rather than having your whole receiver in a single block. You could do that. You could have a huge block, which is IQ data in, packets out, but then you're also not really testing the GNU Radio 4 scheduler or how buffers work. You're just testing it in a very limited way. So modular, many small blocks. It should be suitable for IP communication. So that basically means having a TAN device in Linux you can send IP data through. And that's for 2 main reasons. One, it's easy to test out. There are many applications you can use with IP. You can use ping, you can use iPerf to generate traffic and test your system. And it's also flashy and nice feature, and many people want IP. It's like, how do I send network over my radio? It should have good latency. Coming to the previous point, it's no fun if you want to do TCP and there's 10 seconds of latency. And this has been a huge pain point of Radio 3, as in continuous transmitter. If you have DVB-S2, for example, at low symbol rates, it's difficult to have good latency. The packet size should be flexible. Any packet size should work. Because I wanted to test latency at any different packet size, and that unfortunately means there is no FEC for the payload, because if you define an FEC which is good, I don't know, an LDPC code, then it pretty much ties you to one particular packet size or set of packet sizes. So there is no payload FEC, but there is the provision. If the user wants a fixed packet size and his own FEC algorithm, there's a place to put it. It should use good signal processing techniques, like we're having these packets, they have a preamble, so we should use FFT to detect the packets and synchronize, rather than saying, oh, but I have my Costas loop, and I need to have a long training sequence because you know, the bandwidth, and it doesn't log. It should be production ready, and by that I mean it should run without crashing and anything, and you should be able to go and deploy this in some application, maybe a simple application in industry, where everything is good enough that people will say, yeah, that's good, besides that there is no FEC on the payload. So if you put there an FEC, this should be a modem you can use in production. There is only QPSK for the modem for the moment, mainly for simplicity, but there is also places where you can set your own modulations and codings. If payload FEC is added, this should work at low SNR. So if I add my own LDPC code or anything, then everything else in the modem should be up to the same level of the LDPC code. So the modem should synchronize, it should decode the header and everything else. The payload FEC decoding should be the point at where it breaks if I reduce the SNR. And the modem should also support in the transmitter 2 different modes, which are burst mode. That's when I have one packet to send it, I send it. If I don't have anything to send, radio silence. And also stream mode, which basically emulates how DVB-S2 and similar protocols work, which is whenever I have a packet to send, I send it. Whenever I have nothing, I keep my carrier, I keep my transmission, I keep sending idle frames. And that introduces considerations for latency. Waveform design, I want to go through these very quickly. So it's the most simple design you can imagine for this. Single carrier, RRC waveform, QPSK. The packet has a sync word, which is 64 bits. I've taken many of these ingredients from CCSDS because I come from the space community and I think these choices are nice. So CCSDS sync word. Then there is a header. The header has 32 bits of information. The most important thing in there is 16 bits indicating the packet length. And then there is provision for modulation and coding packet types. So if you want to extend the header, you have room in there to say, I have this mod code, I have these different packet types. You could have virtual channels, whatever you can dream of. Since the header needs to be decoded at very low SNR, and the goal was something like 0 dBs ESN0, I think, there is an LDPC code which I designed just for this application because FEC coding for short block sizes is tricky, and then there is also a repetition code on top of that. Then we have the payload, it's QPSK or other modulation, it's variable size. We have CRC32 for the payload. And then there is this ramp down sequence. So what happens when you have this burst modem, it's not so important if you are using an RRC waveform, but if you want to replace that by something like OQPSK, which is constant envelope, then you want to ramp up the power and then ramp it down at the end of the packet to prevent those power amplifier clicks on the spectrum. So there is the ramp down, basically so that you already see how that can work as part of the system. This is the flow graph of the packet transmitter, and this is how you would see the flow graph in Ground Radio Companion if there would be currently Ground Radio Companion support for GR4. So everything in here is a block in the flow graph, and you have all the connections. This is actually how the flow graph is in C++. So I'm going to go through these very quickly. There is much more documentation about how the modem works in the GNU Radio wiki. If you search for GR4 packet modem, there is like a theory of operation, and you have the description about what each block is doing as part of the system. So to go very briefly, packets coming here on the packet ingress. Then you send a message to this header formatter for each packet, because you say, I need you to prepare a header for this packet size and perhaps for this packet type, for this modulation, whatever. And then you treat the header and the payload on separate tracks. You have the CRC. You might have the payload FEC. So this is not implemented, but if you implement it, you should put it here. Then there is this packet mux, which is concatenating header and payload. You unpack, there is this scrambler. I didn't mention it, but in any kind of modem, you should have scrambling. The header is generated as a vector source, which keeps repeating the sync word is generated as a vector source, which keeps repeating the sync word pattern. And then you have these mapper blocks to modulate, so to convert from bits or pairs of bits for QPSK to complex symbols. These things in yellow are only present in burst mode, so all of this is about the tail at the end of the packet for the ramp down sequence. And then you have these packet mux to group all the symbols together. This thing in blue is for stream mode. So for stream mode, basically you are converting your PDUs. I'll come to that later, how this is organized in packets. So there are PDUs as in GR3. So you are converting your PDUs into a tag stream that it's a continuous stream, and you can send it to an SDR. Then you have this interpolating FIR filter, which is your RRC filter. And only in burst mode, you have this burst shaper, which is the one applying the amplitude pattern. For the receiver, as I mentioned, the first thing the receiver does is to do an FFT correlation with the sync word to detect the presence of the packet, estimate everything you can estimate, so amplitude, phase, frequency, timing, which is the sample in which the packet starts, and also the fractional sample delay, because you want to be very accurate, doing matched filtering on the receiver. Then you correct the frequency error you have estimated, and you correct for the amplitude. Then you do an RRC filter and down sample to 1 sample per symbol. And this is open loop. So you have estimated with the synchronization word where the packet begins, and you keep throughout the whole packet at the nominal symbol rate. So there is no closed loop recovery for symbol timing. For phase, there is closed loop recovery because you really need it in this kind of system. So there is a Costas loop. The Costas loop is seeded with the phase estimate from the sync word. So it logs really fast and really well. And then it keeps tracking phase through the whole packet. So it must know what is the constellation for the payload and for the header and everything. And the sync word is used as pilot symbols because that's a known pattern. So this is how the flow graph looks like. We have the sync word detection, then we have this coarse frequency correction, symbol filter, the sync word wipe-off, so that's where we remove the changing pattern of the sync word. And here we have a very important block, so I will make emphasis here. This is called payload metadata insert. So what happens with this block is that at the beginning of the payload, it's going to insert a tag saying a few things about the packet. What's the packet length, what's the packet modulation, etc. Because the blocks down the chain need that information. However, what happens is this information is actually contained on the header for the packet. So until I do not decode the header for the packet, I cannot process the sync word. I cannot process the payload because I don't have that information. I cannot insert that tag. So what happens is the packet comes along. This is going to pass the header to the output. The header will go through the whole demodulation chain. It will be processed. I will come back to that in a moment. And once the header is decoded, we have this header parser, which is interpreting the information on the header, making a message with packet length, modulation, packet type, whatever, sending it back to the payload metadata insert, which is blocking. It's not sending any of the payload symbols downstream, but when the message comes here, then it can add the tag onto the output stream and begin sending the packet payload. So that's how it works. And for demodulation, we have the Costas loop. We remove the sync word here because we do not need it anymore. It has already trained the Costas loop. We have the Constellation LLR decoder. So you go from complex symbols to basically log likelihood ratios for the bits, so soft bits if you wish. This is an interesting block because it's only implemented for BPSK and QPSK at the moment. You could add any constellation you want. And the interesting thing about it is that it changes the interpolation factor at runtime depending on the constellation. Because if you think QPSK is one symbol comes in, then you have 2 bits coming out. 64 QAM would be one constellation symbol coming in, something, 4 bits coming out, or whatever, or 6 of them. So yeah, that kind of works. With the current GR4 runtime, there are some rough spots just when the change happens, but it almost works. Then you need to descramble. There is the header payload split because, again, header and payload go through separate tracks. You FEC decode, so there is the LDPC decoder for the header. And on the payload, if you are doing any FEC, you would put the FEC decoder here. And finally, you do a binary slicer to obtain heartbeats. You pack 8 bits per byte, CRC check, and if the CRC is OK, you say, here's my packet. So this is how it works. The complete modem can be integrated in any kind of system. So here I have an example of transmitter and receiver using SDRs, but you could also do like only software loopback simulation with channel model in the middle. There is also an example like this, and you can run it right away. If you have a Linux machine with Docker, you can Docker pull this GR4 modem, whatever, and there is a quick start guide on the README, and you can hit run and run something similar to what I'll run in a second now. So basically, you have your ton source. This is where your IP packets come in. You have the packet transmitter, and then there is something to control latency. So basically, this is Matt Edu's talk in GRCon 2019. He was speaking about how to manage latency by limiting the number of samples or packets that go into some part of the flow graph. So basically, when some packet goes out to the SDR, a message is sent back to the ton source saying, OK, this packet is clear, now you can send more stuff. Because if we do not limit the amount, if you try to send a lot of IP packets, then basically the packet transmitter gets full of thousands of IP packets in buffers, and you have hundreds of seconds of latency. So there's something that needs to be done. Here it's done at the flow graph level with blocks which are aware of this. Maybe a custom scheduler which knows when not to call the ton source because there are already enough packets in the flow graph would also help here. So that's an interesting concept to experiment with. And finally, you go to the SDR. On the receiver, it's easier. Oftentimes, latency is not so critical on receivers for these kind of systems. So basically, SDR, packet receiver, there's this packet type filter because you need to throw away idle packets. And finally, you go into the ton sync. So now there's the demo. And here on the table I have 3 SDRs. There's a USRP, which is going to be the transmitter. There's an RTL SDR, which is going to be the receiver. And I also have a Pluto SDR, which is running my SDR. You can see it here. That's basically to see the spectrum. The way I'm going to run this is for the receiver, everything is GR4. So there is already a SOP block. It can run with the RTL SDR, 2.4 megasamples a second, 4 samples per symbol. So this is a 600 kilosymbol thingy. And this laptop is 13 years old. So this is not a new machine. On a new machine, you can run faster symbol rates and nicer things, right? So transmitter, what I'm doing is there is not a transmitter block for the USRP on Gurun Radio 4 at the moment. So I have something which writes on a FIFO, and then there is a GR3 flow graph which reads from the FIFO and basically writes on a UHD sync. So I'm going to run this is the GR3 flow graph, which reads from a file. In this case, it's a FIFO, and writes to the UHD. I also have these plot symbols, so come back to that in a second. This is some simple Python script which receives symbols from the GR4 modem through 0MQ and plots the constellation. Just because we don't have any GUI blocks within GR4 at the moment, so that's a simple way to plot your constellations. Then I have my transmitter, so I basically say packet transmitter right onto test FIFO, and probably I can move this to the other window. And next I have my receiver. So it says it's found the RTL SDR, and I think it's going. So if I run a ping here, maybe a word about pinging myself, because this is a single machine, so I'm using Linux network namespaces to ping myself through these whole radios. Because otherwise, if I say ping yourself, Linux will say, yeah, this is the local IP, there you go, and not send anything to the radios. So you can see ping is going, you can see the packets there. Latency is about 100 milliseconds, which is good, not great. I think most of that is because of the FIFO, which is connecting to GR3, and also because of this laptop. If I run this at home on my much more capable desktop machine, it's 50 millisecond latency, I think. Also here in the modem, you can see there is this user data decoding, so you have like all the information in the header. Something else we can play with, so you can see here the constellation, and now it's very clean. So what I can do here is drop down the amplitude, and now it is horrible. So basically we don't have any FEC on the payload, so the ping is no longer going, but you can see packets are still detected, and you can see the correct packet length. So the LDPC on the header works even with this very low SNR signal. If you add a nice LDPC code on the payload, it will also work. So I think I had something like 70 here. Something else I should show is iPerf, because this is mainly the way I test like the system end to end. So basically iPerf, I'm sending TCP data, and you can see there are a bunch of packets. Probably I should close this Python script, because plotting many packets with Python is not the best idea. But you can see the signal here. This is like an average power plot. So now that we have a continuous stream of packets, you see a stronger signal. And you can see basically this is working. It's doing 1 megabit per second. There are some retransmissions, but probably no packet loss. So this is working. Something you can notice is the RAM usage is slowly increasing. If I keep this going for a longer while, then I might eventually run out of RAM. So that's one of the things that currently needs to be fixed. And probably here I've hit one of the receiver bugs. So you see the TCP is no longer going, basically because it has sent one packet and it's not getting any replies. There is currently some bug we are working with the FAIR team to solve about buffer state corruption that happens at some point. So
Daniel,
yeah.
hi. Can I ask something? That's great work, by the way. I'm just curious if you can start iPerf transmission again and adjust with the receiver gain while the packet is coming to see how much it can compensate for amplitude variation. Because I understand you didn't use any automatic gain controller or whatsoever, so it may disrupt
yeah.
Costas loop and
Good
you know,
point. So
some, yeah.
within the packet, it doesn't compensate for amplitude variations. It takes the amplitude at the beginning of the packet. So if you have a very sudden amplitude change throughout a single packet, which is short, then that packet might fail to decode.
Okay.
But you know, the
But
next
for the
packet,
rest of it, it's, yeah.
the
it's-
next packet takes
next
the
packet is different.
correct
Okay.
amplitude. Do I have some more? 5 minutes? Yeah, great. So, yeah. I basically want to give a few feedback notes about what I have learned through this project about GR4. So, nice feeders. Processed bulk calls are chunked using tags. So, if you have a tag, you are guaranteed to have it on the first sample of your call, with some exceptions. And that's nice in many blocks. It simplifies the implementation of the block, but it's maybe too much overhead in some other situations where you don't even need to look at tags. So perhaps it should be an opt-in feeder, I don't know. Something else I'm doing, and I think this is not really the way it's intended to be done, but I think this is nice. You can use messages with regular ports rather than with message ports, because you can have regular ports with any data type. So that data type might be a message as well. And the reason I do this is because with GR3, often you have a block that receives a message, and then you want to use something about the message in the work function. So you need to store it somewhere else, because basically you have two functions. In here, you're going to have your work function, and the message comes in through a regular port, and the data is already there, and you can use it. So for me, that's been much nicer, and it works. So something to think about. Also, rational resampling ratio. We have it as a first-class citizen on GR4. In GR3, you only have decimation and interpolation. So that's nice. And the history buffer, I think, is fantastic, not only as a replacement of GR3 history, but also for other stuff. For example, in the FFT detection block, I use it because if I see a correlation peak, I cannot say, OK, this is a packet, because maybe 10 samples afterwards comes a much larger peak. So I need to wait on. And I wait on through a history buffer, and I put all sorts of metadata in there. So that's great. Some shortcomings I found. Tags are too expensive. So on the packet transmitter, I was at first using a packet length tag at the beginning of a packet, so kind of a tagged stream thing. And it didn't work properly because it was so much overhead. What we can use instead is vectors. So that's called PDU on my code. It's called packet on core. Basically, it's a standard vector where you put your packet. There are some maybe not nice things with that. So by default, you get buffers which are 65K elements. And maybe you don't want to have 65,000 whole packets in your buffer. You could have smaller buffers, I understand, like even 2 elements in the buffer. with these large buffers, there is a lack of back pressure because, the buffer only fills up with 65,000 packets. And then something about memory management. So you have these standard vectors rather than, scalar types. Who deallocates the unused packets? Is it constantly allocating, deallocating? All sorts of questions for me. Also general blocks. So there is no forecast function at the moment, and it is not foreseen. There is an async port, which means this port might do anything regarding resampling. And in most cases I've used it, it works, but it might not be enough in some cases, I think. Coming from GR3, there are some cases where forecast has been really important to make the block do exactly what I wanted, so I'm not really sure, especially when you have a block that sometimes can produce output without an input and sometimes cannot, so how do you communicate that to the scheduler? Also something else, there is the single-threaded scheduler, there is the multi-threaded scheduler. The demo you saw before is single-threaded scheduler, and the reason for that is multi-threaded scheduler crashes with most of the flow graphs I've written. And I don't know why. It's basically some tag that should have arrived doesn't, so the block crashes. And then there is some buffer management bugs, and you saw one of those in action. And finally, a fun experiment we did. So this was with Frank Seppenfeld from ESA, not ESA Germany, but ESA Netherlands, ESTEC. He works with the satellite communication group, and he reached me in the summer saying, oh, we have 1 megahertz of geo-transponder bandwidth because we are doing some tests with industry. Would you like to test your GR4 modem on the satellite? And I said, yes. And the way this works out is they have everything for downlink set up at a German ground station with a very large antenna, but you need to do the uplink on your own. This is 5.9 gigahertz, so here am I at home with my Wi-Fi antenna, 2-watt Chinese power amplifier from AliExpress, and you can imagine the SNR you get out of this is not very good, so this was 125 symbols per second to get an SNR of between 9 and 10 dBs, which is the thing you need to decode with no FEC, some short ping packets. And then the interesting thing is this is 5.9 gigahertz with this USRP, no GPSDO, no nothing. So the frequency oscillates like crazy, and I needed to tweak all the Kostats loop parameters, but it worked great. I was like testing at night and, change, recompile, run, and it ran. I will put up the SIGMF file of this probably this afternoon for all you to play with. And that's all I had.
Thank you. We're a little bit over time. It's a pity because I think that this deserves a lot of discussion. It's very, very nice work. But in order for us to eat early, what do you mean? Okay, we can do that, yes. Who thinks that we can start lunch a little bit late? Raise your hand. Okay, so this is decided. So maybe we can take in some questions.
So how's the debugging experience in GR4? Like you said, you couldn't debug the crash. That is unusual for you.
Yeah, so one thing I found is with GDB, if you get a crash and you try to print out the stack trace, it's like pages and pages of templates because the name of one function might be like one whole screen. So that's rough. The way I'm mainly debugging is I have prints on each of my blocks at the beginning of the work function or process block function, which are with an if-def, so I don't have those on production, but I have like trace printing. And this is very helpful because I print the number of items that comes into the block, internal state of the block, and that helps me get an idea of how everything's doing. If I run on the single-threaded, it's even easier because, there are no things running at the same time, so a priori I don't know the order in which things get called, but I see it on the trace log. So that's the main way I'm debugging.
Thanks.
Maybe I have a question. Have you tried this on an even slower computer?
Ore?
Have you ever tried this on a slower computer?
No, this is the slowest one, which, by the way, if you want to know, it's an i7 but 2000 series.
Okay.
So 13-year high-end laptop.
It would be interesting to see, because this is quite impressive, by the way.
Yeah, it would be nice to see this same thing, Raspberry Pi 5.
Yes,
I don't know how well it compares to
That's
to
what I
this
was
laptop.
thinking, yeah. Any other question? Oh,
Just a comment for GDB, because obviously we are using the variants of a lot of types inside, so you get a huge signature for anything. GDB is Python scriptable, so you can easily create your own backtrace function which filters out the contents of the RVA variants. And if you need it, I can send it when I get back home, because obviously that's a thing that you need to have to debug this code.
Yeah, that would be awesome. Also, I found that issue in perf, so some of the profiling I'm doing with perf, and sometimes you have a function which it's clearly the name of the block, sometimes you have a function which is like really long and you cannot even copy and paste. I needed to go into the HTML code with Firefox Profiler.
Any more questions? Oh.
Hi, thanks, impressive work. Forward-looking question, what will it take to go to higher modulation orders? How would you approach that?
So it somewhat depends on how much do you need to track the phase. That would be the first thing you need to think about. If you want to do 16 QAM, are you going to do decision-directed costless loop kind of thing? If that works for you, it's quite simple, because then basically you can extend the costless loop, which is in there, to support the 16 QAM modulation, and then it's really just another case, because the current costless loop is doing both pilot for the packet preamble and QPSK. If you need something fancier, such as distributed pilot symbols throughout the packet, because you do not want or cannot do these 16 QAM costas, then probably you need some other blocks which look at these pilot symbols, insert tags with the phase information, and maybe something that looks forwards and backwards. When I've dealt with these systems, what I have is something that basically measures all the distributed pilots, and then something that linearly interpolates the phase and everything between each two adjacent. So that's even more tricky to get going, because on the input of your blocks, you need enough samples to be present so that you see the next phase estimation.
Do you have any way to compare this to like something similar for GNU Radio 3 for performance?
No, unfortunately not. I have something simpler, which I intended to be like a fair comparison, and that is a QPSK transmitter. So random data, QPSK modulator, and RRC filter. And I have that in GR4, I have that in GR3. It's a very simple flow graph. GR4 is like 4 times faster, 5 times faster, something like that, than GR3. But the reason is silly. The reason is GR3 is calling Volk for the FIR filter, and the FIR filter is 12 taps or so. So it is very inefficient to call Volk every time for such a short filter. If I were to code the same block in GR3, then that would probably be a fair comparison, and I think it would be more or less the same, because in this case, most of the work is on the FIR filter math. So any bad scheduler you do in GR3 is not going to show up.
Okay, I suggest that we move on to the short presentations, and then you can still take your questions during the lunch break. I'm sure that you have many. Okay. I just need to find the presentation. Yeah, it's right here. Yeah, this is it. Okay, the floor is yours.
One, two, three. No? Yes? It's this side? Okay. Thank you very much. Well, it's a great pleasure to be here. Thank you very much for inviting me for a lightning talk. I was more thinking about lightning talk to be something like a lightning, but it turned out that it's about the time duration. So excuse me if it's not really lightning, but I've been given 10 minutes, so I guess we can start. So thank you very much. So this is a very boring talk that I'm going to give you today, of course, because you know GNU. This is the original title. GNU radio-based SDRs for isotopic and isomeric mass and lifetime measurement in heavy ion storage ring, and boring. But then I was thinking, okay, Eric Blossom gave us such an inspiring talk at the beginning, so maybe I should change the title to something like this one is not. So maybe I should change the title to Reaching to the Stars Using GNU Radio. So I mean, why not, right? So, but there is a bit of truth in this, because this is from all of the, you remember from the nice tour that Jens gave yesterday, and also some of the people that were with me. We were walking around the GSI tour, GSI facility, and to see what is happening. And also from the very beginning talks of Peter Spiller and also Jens, you got this information, or got this taste of how GNU Radio can actually help us on all aspects of the research, fundamental research here at GSI. So what does it actually mean? Basically, we are interested in elements, and elements, we want to know. Everybody knows about the standard elements. This is the periodic table of elements that you everywhere see in the schools and the universities. So this is a very good thing, because it contains all of the elements according to their chemical properties. But there is some information that is missing in the standard presentation of the elements, and that is that every element exist there because of the certain number of protons that they have. But what is much more important is that they can have different number of neutrons, and this is called the isotopes. So that basically every element that you see here in the table on the left side has basically a number of different isotopic configuration. That means, for example, lithium has only 3 protons, but it can have 3 neutrons. It can have a 4 neutron version, a 5 neutron version, so that you have the overall lithium 6, lithium 7, lithium 8, and so on. So if you basically make a 3-dimensional map of this picture on the left hand, you can see here that this picture that you see here is just one layer, that every element in fact has a lot of different isotopic configuration. And that's very important for us from many very different aspects, from the biological aspect and also from the point of view of stellar evolution. And that's one thing that people in the nuclear physics and nuclear astrophysics community very much like. So instead of using this picture on the right side, and people redistribute this map into a much more readable map, which is called the nuclear chart. And the nuclear chart immediately tells you all information, because it tells you that if you have the number of neutrons here and the number of protons there, you have seen this picture in Jens' talk at the very beginning, you see that all of the things that you saw in the previous, the stable isotopes, they are here in the black line. And then, but you have for every element which is named here, you have basically a distribution of different isotopic configuration that you can have. So you can have a more proton-rich, you can have a more neutron-rich. The blue ones means that they have more neutrons. The orange ones means that they have more protons. So it's a very important picture because all the nuclear physics, nuclear astrophysics community can immediately see a lot of things here. So you can have the super heavy elements here, GSI expertise. You can have the proton-rich. You can see how the things. Why is this only so narrow? Can it be? Why there is nothing here? Why there is nothing here? Because you cannot have an element that has a lot of neutron but has not so much proton. So there's a lot of information here. And of course, if you like, you can have a free, there is a free app for Android and iPhone. You can just download it and just play with it. You can zoom in, zoom out. It's very nice. So I hope everybody knows what IAEA stands for. No? International Atomic Energy Organization, Association, yeah. So that's from the United Nations. So this is the official app of the United Nations for this. But this is so important for the nuclear physics community that people even don't have the time to spell out the nuclidic chart. They usually call it the nuclidic banana. So this is the jargon, the official jargon in the community. But where do actually the elements come from? And that's the most important question that we are interested in. Because the core of the elements, there are many different possibilities. So we start the so-called the Big Bang nucleosynthesis. So you have to have a starting point, and this picture is one of the most stolen slides in the community of nuclear astrophysics. So this is like a mixer jar of universe. So you can imagine that everything there is in the universe is inside this jar, and here outside there is nothing because the whole jar basically contains the space and time, whatever, you know. So, but that's the only way you can actually present this, is that you have different stages of the universe, the evolution of the universe. At the very beginning, you have the Big Bang. You have enough pressure, you have enough temperature where you can create the very first element. But then the universe gets very fast, very cool, so you cannot process. And then you have the first stars, which are so-called low metallicity stars, and then later you get more on and on and on. So until you get the different stars and galaxies and formations. So basically, the stars are the birthplace. The stars are the birthplace of the elements, and that's where we are. What we are interested to do is that we want to know that across the nucleatic chart, what kind of process, be it like accretion, white dwarf, we have some burning stars, we have some supernova explosions, type 1s, type 2s, we have neutron mergers. So how exactly this nucleatic chart is being processed. And this is the same nucleatic chart, as you can see here, that there are actually several different processes in action. So you have the Big Bang nucleosynthesis, you have the S process, the slow process of neutron capture that can happen inside a neutron wind in the universe. You can have the rapid process. So if you have a site which is just standing there and suddenly a neutron star explodes, suddenly a supernova explodes, and there's a huge amount of neutron wind, then this starts to burn. But as you can see here, if you look along this line through the thing, that's called the value of stability. Basically, you're looking at here. And this means that the way that the nature is producing the elements is just going staggering. So what it does, it never goes up like that. So you never start from hydrogen and helium and suddenly create gold or titanium. So what you do is that you just stagger. You go a little bit right, then fall back. You go right, you go fall back. You go right, you go fall back. So this kind of staggering mechanism. And this is very easily visible here, if you can see here, that these are actually higher in energy. That means people try to go up and fall back. The evolution of the elements always goes forward, but it never goes on the valley itself. It just goes up and down and up and down and up and down and up and down. And this means that you have to do this because otherwise you cannot just go a straight line. The problem with this is that the stages where the elements are trying to evolve can be temporary. It's as if you want to try to climb a ladder, but your bars here, any of these bars or any of these holes, is just available for you for a couple of milliseconds. So you either manage to climb up within that couple of milliseconds, or you cannot reach that energy level. So that means if you want to create a gold, you have to have a certain energetic path through the isotopic configuration, which allows you to actually traverse that line of energy. And not only that you can do it, but you can do it in the right time. That's why, apart from the nuclear mass and the reaction cross-sections, what is very important for us is the lifetime of the isotopes. And that's what we want, and that's what we want to do with junior radio at GSR. So this is GSI, you know this. This is the GSI fish. This is a very long-lived, rare species here at GSI. It used to live here, but since Ralph started to build his FCC here on this building, it's a running joke. So this building. This is being is being built here right now. There used to be a pond over there, so this fish used to live there. But everybody has promised the fish to get a new pond in the new fair. So that's that's another thing. So this is exactly the same picture again. So you know that we have the source and accelerator and everything, so you know already this picture. Again, the same. So what we do is that we want to inject into the ESR, and the ESR is now shown here in a much larger picture. And we have here a couple of non-destructive detectors that you can see here. By the way, I also teach the art of self-citation, so in principle, if you're interested, it's $50 an hour. So, so we are using this non-destructive detectors around in order to record. So we let the particles, we inject the particles into the storage ring, so we let them go around as long as they want, and as suddenly, if there is a kind of a lifetime, there is a kind of a disintegration, then we can exactly measure this. How do we do this? We have a chain of signals, analog signals, low-pass filters, band-pass filters, and everything. And of course, we use data acquisition. Unfortunately, up to now, the standard commercial ones, I have seen. This is running with LabVIEW. These are some good spectrum analyzers, to be honest, but the problem is that they are not scalable, and they are very, very expensive. So how does a picture like that look like? So this is a spectrum of all the possible lines that we can see. This is a two-dimensional. Two-dimensional spectrum, and you see all possible nuclear isotopes that you can see after an injection into the storage ring. You can zoom in. You can zoom in to get more data. You can even zoom in to see the isomeric contamination of the individual isotopes. So what is so nice about this thing is that if you watch this two-dimensional spectrum, which is acquired by an RF signal from those detectors, for example, from this detector, you can make a waterfall diagram like we had this here, and this waterfall diagram shows that time. Okay, in this case, time is coming from up to down. So you see that one particle, actually two particles, are coming down, and suddenly, after it's a short time Fourier transformation, it's a short time Fourier transformation, it shows that suddenly one of them decays. So that basically the first time signature shows the lifetime of the first isotope, and the second one that. And if you continue doing that, even with a newer, so this is basically the same position. So if you continue doing that with maybe a little bit more sensitive devices, you can even much more exact say, okay, these were two particles here. One of them, after about a second, one of them decayed, and after a couple of seconds more, the other one decayed. So you have two. This is basically the transition from one of those blocks. If you imagine the value of a stability, it was just whoop, just slip down one block from here to here. So one isotope changes its nuclear constitution from one thing to the other. So this has a lot of information for the physics community. Everybody is very happy about that. But of course, we do all this analysis using Python. We do a lot of calculation in the green cube and everything. But where we have also analysis code on thing. But where does this journey go? these are some possible detector positions that we are planning to do in the collector ring at FAIR, and this is where I was actually going to approach Jean-Michel here for this, because this is very much relevant to your, to your talk that you just had before. We are going to, of course, we're not going to put detectors all around this place, but at least a couple of places. So we are, of course, we would like to increase the measurement accuracy by correlating signals from different detectors. Exactly. So this this matrix that Jean-Michel was showing is basically carrying information for us, which is relevant for the exact time measurement. So we really need a white rabbit-based hopefully GNU radio that can take the signal, basically observe the same beam from 4 different locations around the ring, and by correlating by the phase information of these things, we can actually get to much more accuracy in the measurement. So we have also my colleague here, Dr. Chen Wang. She's also here to help us in this respect. So some personal history at SDR. Of course, I mean, back in 2008, it took me about 6 months to make this SDR board from scratch, you know, from schematics and PCB, 100 micron technology, programming the Altera thing. So it took me a lot of time. It's still working because at that time I started in the RF group actually here at GSI. Even at that time, I don't know which version it was, I tried to use the GNU radio in 2008, but I really couldn't manage to connect it to my self-made board, and so basically I switched to the commercial ones up to now, which I hope that I can come back. And this we have done. We've got some experiences, and thanks to Alexander and Ralph and all other people who have, and also colleagues from the ACO department who have created, and also the electronics department who have created the picoscopes, and also the Lime SDR is put into this kind of very nice things. We actually were able to do the first measurements using this. So this is a very beautiful measurement. So as you can see here, this is the thorium. This is a thorium beam, which is standing on top of a couple 4 components. Basically, it's a protactinium, we have the actinium, and a little bit of uranium also on top. So that means you can see this picture here already makes a lot of people very, very, very happy, because this has never been seen before. This is as if you can imagine that this is basically you have a beam of thorium going around, and then you have all these other components that they are constantly taking over and coming back, and taking over and coming back. Basically, they are, for RF people here, they are basically fighting against, the electron cooler is basically fighting against the bunching potential inside the basically phase potential or the bunching potential inside the storage ring. This is an amazing phenomena, so this itself is worth of publishing by itself. One of my colleagues is working on this. Forgot to thank him. That is Konstantin Mohr. I forgot to put his name here. So what we want, future ideas. So what we want is, we are very much interested in one flow graph, one computer which runs actually the GNU radio flow graph. It can have the timing connection to FAIR, GPS connection. We have of course, we have the connection to the high performance computing of GSI, thanks to Thomas Stibo and other people, where we can continuously throw basically right into the luster. We are looking forward to have connection to the accelerator network, thanks to, I think Hanno is there, thanks to Hanno and his colleagues. So, and if we could basically put some picoscope units and SDR unit in one big top thing, that we can control everything through one big GNU graph, that would be amazing. So this is, for example, one thing that we have been testing, and this is going to be the 2025 experiment as well. So you can see that in the previous experiment, we were able to achieve the very, very high resolution that is equivalent of 100 keV energy difference between the nucleus and its first isomeric state. And this is so close, that is the 100 kilohertz, that is amazing. So what we want to do is to monitor to see if so this is the ground state, and this is the isomeric state. Sometimes it comes, sometimes it doesn't come. So for that, we need GNU radio. Why? because 2025 experiment proposal, my boss came to me and said, you know, Shahab, Yuri, my boss, he said, you know what, we are going to hunt for a very, we're here to hunt for a very, very rare isomer. I said, because it comes so, the probability of production is so isomer, that is very low. So we want something that, as soon as we see the isomer, we should stop the accelerator. I said, okay, fine. And they said, what? Stop the accelerator? We have never done that before in the last 50 years of GSI. To see, look at the spectra on the fly, and if you find something, you stop the accelerator to continue measure it. So basically, it's a very, very, very simple GNU-radiograph. So you have some kind of source, then you have a condition. Who's a ham here? 1, 2, 3, 4, 5, 6, 7. So everybody knows a squelch. You have the standard squelch. So I just need one source, which is the hardware. It can be this SDR. It can be condition. One branch is continuously writing to disk. The other one just has a squelch, looks at this picture. If it's one, it doesn't send any signal. But suddenly, if it's 2, it should immediately send a signal. And this is basically like the fencing, you know. So there's a fencing line going on, and we were even thinking of making an acoustic beep because these isomers are so rare. We need people to wake up because otherwise they fall asleep during the midnight when they're doing this. So, and just as a matter of fun, since 2020, we are having our experiments simultaneously monitored by our colleagues in Japan and also in Vancouver, in Canada. So this is something that all people from different time zones can actually take part live. So we were thinking about them making a drinking game out of this. So every time there is an isomer, you have to go for a shot. So thank you very much, and I'm happy if there's a questions.
Thank you. I would like to call the next. Okay, the next. He's already here. Let's do it.
Hello? Sorry?
Yeah, it's okay.
It's okay? Okay, you can hear me? So, I'm keeping you away from your lunch break now, I realize, so I will try to make this really a lightning talk. I will talk to you a little bit today about what we call RF compatibility testing and how we do this at the European Space Agency. Does this have a... Yes. The European Space Agency is responsible for the European Space Tracking Network, which is a network of ground stations used to communicate with satellites. It's operated 24/7 from the European Space Operations Center, also called ESOC. Of course, because we are a space agency, we need to have acronyms and abbreviations to keep the barrier of entry as high as possible. Which is also located here in Darmstadt. Today there are more than 20 different missions supported. They range from near-Earth missions in what we call low Earth orbit. This is a few hundred kilometers up to highly elliptical orbit, which has the lowest height of a few hundred kilometers to a few thousand kilometers. And we have a few missions in the Lagrange points, which are stable regions of the Earth-Sun system. Some are about 1.5 million kilometers away from Earth. And then we have another category of missions which we call deep space missions, which are typically around other planets like Mars, Mercury, Jupiter, and Venus. We have, I will show later that we have many different ground stations that are communicating with each of these type of missions. What makes it a bit special is that each mission is generally very unique in terms of its design and its objective, its instruments, And you can think of it as a custom-made machine that there exist no copies of it. Of course, some missions have multiple spacecrafts, like Galileo, which have now almost 30 spacecrafts. Some of them are also very expensive, with budgets of more than 1 billion euros, like JUICE, which I'm showing here, which is currently in transit on its way to Jupiter. We also have Bepicolombo, which is on its way to Mercury, and we have a mission called Envision, which is in the planning, which will go to Venus. Here you see a map of the European Space Tracking Network, or ESTRAC for short. The blue circles are the ones that are part of the ESTRAC core network, and then we are also collaborating with the NASA Deep Space Network and a few commercial providers and other space agencies. To communicate with our deep space missions, we have a ground station here in Argentina, one in Spain, and one in Australia. For communicating with polar orbiting satellites, it makes more sense to have it closer to one of the poles, so we have located one in Kiruna, which is in the north of Sweden. As I mentioned, because these are pretty much unique, so how do you know that a newly launched satellite will be able to communicate with the ground station? Do you want to wait until it's launched and hope for the best? Or can we do something better? Testing when it's in orbit, I would say, is quite risky. Failure is not an option, and so on. Or do we simply move the ground station to where we build the new spacecraft? It's a bit impractical because it's not always being built in the same place, and the ground station is quite big. We can also send the whole spacecraft to the ground station, but because we want to locate the ground station in a RFI suitable environment, it's very difficult to get, especially a maybe 1 billion euro machine to this location. Unless, by chance, the spacecraft needs to go there anyway, which is the case for our ground station in French Guiana, in Kourou, which is also where we launch the spacecraft from, on the Ariane 5, 6 and the Vega launchers. But of course not all missions are launched from there. Recently we have also launched a few using the Falcon 9 from SpaceX. So what we have since many years now have had here in Darmstadt is what we call the ground segment reference facility, which contains every subsystem from the ground station, representative version of it. And instead of bringing the whole spacecraft to ESOC, we take out the important parts, most importantly the transponder, which is the RF system, along with the onboard computer, which is used for generating data and receiving commands. And we pack it together in this rack, which we call a suitcase, because it's so nice and small and portable, relatively at least. After we have done sometimes several weeks of testing, sometimes even months of testing, we issue a statement of compatibility, which is a requirement before the launch. If we find any problems, either we have to find workarounds or we have to go back to the drawing board, but at least we are aware of it and we don't get any surprises when it really matters. The list of tests we perform is quite long, so it can take a very long time depending on how complex the mission is. The CCSDS actually defines a list of a minimum set of tests to be performed. So there are even more than this. This includes things like frequency stability, measuring the spectrum, measuring frame and or bit error rate, measuring the ability to command, so both from space to Earth and from Earth to space direction, measuring the ranging using the same signal we use to communicate, measuring the Doppler, and also the stability of the ground station. Here are some figures just so you have some idea. The signal levels arriving to the spacecraft can be in the order of minus 155 dBm up to minus 50 dBm, so it's quite some dynamic range. The signal to noise density we have on the other direction can be as low as 20 dBHz up to more than 100 dBHz, depending on how far away or how close it is to Earth. So also some dynamic range there. When we're talking about data rates, we have sometimes as low as only a few tens of bits per second, or symbols per second in this case, up to now soon 500 megasymbols per second. Here are some example results that we might find. We measure the phase noise, we measure the spectral purity, and we measure the frame error rate and compare it to the theoretical or simulated results. All of this goes then back to the operator link budget, not only to have the theory, but to have really the performance of the system as well, to take this into account. This is just a very basic setup. We have the ground station modem connected to a frequency converter to get it to the frequency we want. We have a ground to space channel, which in this case is just some attenuators and diodes to precisely control the level. This goes then to the transponder, which is connected to the onboard computer. On the downlink channel, we have also a noise source to simulate the signal to noise density ratio. Going to a frequency converter again to get it from the RF frequency to the IF, which is what the modem supports. What we have recently realized, to reduce the amount of risk when we actually bring everything together, is that we can do a bit of preparation. If we can only record the signal transmitted from each part, we can actually send it to the other side, which might be in another part of Europe, or even sending it from Europe to the US, in case we are supporting NASA missions. This is done via OneDrive or Dropbox or even email if you have a small file. But of course, as you can see from this, the files are either very large because they have such a high bandwidth, or if we need to measure the frame error rate down to 10 to the minus 8, and we are operating with 10 symbols per second, it will go over a very long time. So this is only something we have recently started with for the Hera mission, which will go to investigate the results of the NASA DART mission. We recorded some samples from the real spacecraft in OHB, which is building the satellite, and sent them to ESOC. For NASA's Roman Space Telescope, some samples were recorded at Goddard and sent to ESOC so that we could do a first test of our new implementation of the LDPC 7.8 decoder. And in both cases, they were played back to our S-Track specialized receiver using GNU Radio and the USRP N320. That's it for me. Thank you.
Okay, yeah. So to all the people on YouTube, we will be a few minutes late. So I think we will start in about 1 or 2 minutes. I think we will start in about 1 or 2 minutes. Yep.
Okay, so
May I see?
no signal.
Yeah.
Okay, this one is good. So welcome back, everyone. Just to remind you, we have two simultaneous tutorials. There's the one over here on SIMD, but there's also the one on the other room. So if you're more interested on the other one, you have to go over there. It's on the other building. So I would like to help invite Matthias, who's going to perform the first tutorial on SIMD, right? For GNU Radio 4. So the floor is yours.
Thank you. So let me start with the idea of what this will be about, the session. First, I want to introduce SIMD. I expect many of you know what it is. Some of you may have heard it, but don't know the details. I hope I can get you all on one page here. Then I'm going to go to the data parallel types, which implements SIMD from the programming language side. and then I will show some extensions to that. And then finally we come to something that goes into how this is relevant for GNU Radio. I will do a very simple example and then show how this is important in the context of merging blocks, and how merging blocks and SIMD somehow go together in a way. One of the goals for this talk is that this is for you. So if you want to follow along and you get lost at some point, please speak up, unless you want to get lost anyway. But let's make this as interactive as is useful for you. If we don't make it through all the material, then so be it. But it's more important that I don't lose most of the people here, then it's not useful. Okay, so why are we talking about SIMD? SIMD is short for single instruction, multiple data. What this means is that you have multiple operations, so a plus is an operation, in one instruction. In other words, that means you do the same work in less time. Or as a picture, you have all these additions, one after another in time. Now we block them together. And you see you have higher throughput, lower latency by doing that. So this is a feature of our processors. But there's another feature that is very similar. It's called instruction level parallelism. What this means is you execute multiple instructions in one CPU cycle. Or in other words, you execute the same work in even less time. So as I put in that picture, the block with those 4 additions, I put another one at the same time. So even more throughput. And the idea of the SIMD type in our language is to express data parallelism, so a bit more abstract than the actual SIMD instructions. And that data parallelism then can be translated into whatever the system, your CPU, can do. And that is both SIMD and instruction parallelism. I showed this on the slide. Actually, the stdx that I use there for the type is a shorthand for std experimental. That's because the type that we're currently using is not in the C++ standard. It's another ISO document. It's a so-called TS, technical specification, which is kind of a better version of what goes into the standard. So we're expecting that C++ 26 will have a SIMD type, or somehow named that way. For now, it's STD experimental SIMD. It is shipping in GCC since a few years, and there is my library SIMD that we are also using that abstracts that dependency on GCC away so that you can use it portably with other compilers and other standard libraries as well. All right, so to continue motivation here, I wanted to show an example of how we can reach peak flop. Flop is abbreviation for floating point operations, typically measured per second or cycle. In this case, I want to look at this per clock cycle of the CPU. What's behind that example here is something we typically do. We give our compiler sequential scalar code. And then the compiler can't do anything useful with it. It cannot create any SIMD code out of it. It cannot invent parallelism where there is none. If you have this chain, dependency chain, there is no parallelism to extract from for the compiler. And so this is a completely made up example and not useful at all. But it is good slideware to explain the problem. And it's not that far away from probably a Taylor series expansion, right? You often have these multiply add sequences, and you have the result of that going into the next multiply add sequence. A more realistic example, of course, would use different coefficients for every iteration. But to make that simple, and also to make Google Benchmark happy because it wants to execute the loop as long as it decides is necessary to measure properly. Yeah, I just reuse the same constants there. And it makes it much easier to actually reach peak flop, because reaching peak flop in serious real code is so much harder. But it's an interesting exercise. So what this benchmark does, it just creates one float object, initializes it to 0, and then the fake modify is some optimization barrier, basically telling the compiler, please forget that you know that it is a 0. You still know it's a float, but you don't know the value anymore, because if it knew the value, then it could compute all the steps, right? And then the Google benchmark decides how many iterations it does. And then in the end, you're saying, well, compiler, I'm using that value, right? Because otherwise, the compiler would say, you're not using it, it's dead store, I'm going to eliminate everything that comes before. And so your benchmark would be really fast. So I need that fake read. I could do something else and use it, but then I would measure that in the benchmark. So I'm faking everything here. Those are just tricks with the compiler. Now if I compile that and run it, you see I measure 0.25 floating point operations per clock cycle, even with O3 and basically all optimizations on. And then if I turn on this march equals native flag on this machine, I get a speed of a factor of 2 already. I'll come to that in a bit. So compile flags matter. We noticed that. But now let's just change the type. I'm going from float to a SIMD float, and note this is actually using STD-SIMD, so that's the prototype for C++26. You will not be able to replicate exactly that code for now. But the basic idea is you go from float to a SIMD float, and now you have multiple zeros. Again, not useful. But you could initialize this with different data. You have your array of data, you take that whole chunk as initialization, and then you do the same process. I mean, a Taylor series, all the coefficients are always the same. It's just the input data that is different, all your measurements that are different, right? And so that is realistic thing you would do. You would just take a bigger chunk and then calculate this on a lot of inputs at the same time. So what this type here is, you're saying, give me a default SIMD float, which the implementation chooses for you, knowing what your target is. And you ask it, what's that size? And it says, in this case, because it's compiling for an AVX 512 system, I can put 16 values in there. And then me, as a person who knows how my CPU works, I say 16 times 8, please. I want more. And so 16 times 8 is 128. So if this sounds like a GPU to you, yeah. So we're doing 128 floats basically at the same time, in a hand-wavy way. And going through that benchmark loop. And if I compile that and run it, you see we're getting 8 flops without the march flag and 64 flops per cycle with march native. So a speed of 256 compared to the naive loop. So what happened here is this 0.8 times 8, it increased our instruction level parallelism by a factor of 8. Because the SIMD width, which is the SIMD float size, is 16. This is also already a good speed up, but there's so much more in the processor. And this is a tuning factor, something that you, in many cases, have to try. Because it's, well, there is an architectural thing that you could theoretically derive this, but the more complex your code becomes, the harder it is to see how much instruction level parallelism is still available for you to use. And if you go too high with that number, then things could become inefficient again. So it's not always very straightforward how to do this in a performance portable fashion, but at least there's an interesting tuning knob that is easy to reach And it is easier to reach in C++26 than it is with the current TS, but it is also possible there. So the reason that first implementation was slow is because there was just no parallelism. It is just one long dependency chain. We need a mic over there. I think that one's not working. Where's the blue one?
So just to back up a second, so this you're getting this because there's like in this particular processor you have two ports, two FMA ports.
Yes.
Okay, good. Just to clarify the obvious, not so obvious, because it depends on the machine.
Yes.
Okay, but it can issue 2 per clock or whatever.
Yes, that's totally dependent on the machine. So there are Intel processors with AVX 512. Some of them have 1 FMA port, some of them have 2 FMA ports. That makes a difference in terms of IOP. One of them wants to have a 4 there, the other one prefers to have an 8. The 8 should work for both of them. It's just that the speed up you get is different for those different processors.
So how, is there any tooling to look inside to see, like for Intel compilers, you get like this nice tune thing where you can look inside and see, okay, this pipeline is mostly running empty. Is there something similar in the GCC LLVM world?
So I will show something in a bit where you can get an idea of parts of the code. It's basically you need to look at smaller regions of your code where you have the loops and then try to understand what is my instructions per clock cycle, right? That is the thing, the number you need to look at. And then you always have to know what your CPU can do, because without the knowledge of the theoretical reachable number, that number is kind of useless, right? Of course you want to get it up, but if you don't know what you could reach, it's so much harder. Yeah, I will show something, how I typically go about it, at least. Right, and the other thing is this march flag. If you don't tell your compiler where you're going to run your code, the compiler has to assume, well, that's the architecture. That architecture evolved over time. I cannot make use of the new things because you might want to be compatible to the old things. And especially with x86, there's a huge evolution. 2006 basically is when the 64-bit architecture came out, and you had SSE2 in that. So that's the baseline for 64-bit. And if you just compile without telling the compiler what your machine will be, that's what you're going to get. That's 2006. And that is pretty low on that graph. There's a factor of 2 that we were able to get just with a bad code already by putting the march flag there. And that happens on GCC. It doesn't happen on Clang because it contracts the multiply and the add into a fused multiply add instruction. Clang doesn't do that by default. You have to pass another compiler flag, fp contract equals, and so on. That's because they interpret the standard differently on whether that is something they may do or may not do. And I have been trying to resolve that issue also in the committee, but so far we were like 50-50. Need to write another paper. And so really important here, if you have a very capable machine that you're going to run on, you really, really want to turn on these march flags to get the AVX 512 instructions. They are so much more efficient. Even if you don't want to make use of the full width of the register and just want to use half of it, you still want the instruction coding of AVX 512. And just recently, the Zen 5 architecture was announced. Don't know if you've seen that. Zen 5 has a 2x speed up compared to Zen 4 on AVX 512. So by now, Intel is walking back from AVX 512. They don't want to do it anymore. And AMD, like, yeah, we got the speed. So this is super important. And I'm not sure yet whether Zen 5 has another 2x up that red line. I did not understand it yet. Yeah.
Maybe just to inject a question or a hint for the people who are going to package GNU Radio. This is very critical, whether you say you do a generic installation that runs anywhere, and then as you said, like it will be stuck with the performance of 2006. Or you say like you branch out, that you compile for different architectures and fall back to the slowest one that the computer supports. Or I throw in like another suggestion that we should maybe discuss about just-in-time compilation, where you have like a base installation that has okay performance, but then that the SIMD is recompiled on the fly.
I mean, the first thing is I would paint the first thing differently. You can either package software or you don't, right? If you package software, you need to support the platform that your user has. So that's not an option. I can't package something that needs a Zen 5 now because no user will have it, right? The other question that I ask is whether is there some infrastructure to build multi-microarch binaries so that I don't have to do in-time compilation.
Yes. Yeah. So glibc, the dynamic loader, has infrastructure for that. Below the lib directory, there is another directory structure for different ABI versions. And that's basically SSE, SSE4, AVX2, AVX 512, and so they have it not as fine-grained as the march flags are, but at least the vector width. And so what you could do is you put everything of your application into a lib, a dynamic lib, and then you have a very small executable that is just linked to that. And then the dynamic linker will go through that directory structure and try the first one that your system you're running on supports. If it doesn't exist, it goes to next and so forth until it gives up and doesn't find anything in there, and then takes the normal lib directory, which is the case for almost all of it. But if you ever look at this with strace, you see that it looks at all these strange directories when it's trying to find the lib. And that's where you can, at this point, as far as I understand, package things in a way that can already make use of this.
I have one question. Do you have any speculation why Intel may have dropped it and then AMD picked it up?
Maybe we do that speculation afterwards.
Okay, great. Thank you.
I do, yes. So, actually, I want to say that I think we write and use code as impossible as that first example all the time. A very prominent example is all of CMath. You have these functions, they have this library boundary to the C library, you give it one value, you get one value back. And so what the compiler does, because this is so bad, is the compiler sees, I know that function. I'm just going to replace that with a built-in. And that built-in, I can optimize everything out of this. Because I know how it's supposed to behave. And I completely ignore that the library has an implementation. I mean, I can use it if I don't want to do some optimizations. But so what the compiler can actually do here is if you put on FastMath and O3 and GCC, it will pick up a different implementation. It doesn't take the cosine float. There is a cosine that takes SSE vectors, that takes AVX vectors, and so on. So that's the auto-vectorization of those CMath functions that the compiler can do just because it knows those functions. But your functions will never become part of the compiler. So as long as we write these interfaces, we have that problem. So the function is often the inhibition for making use of SIMD and instruction level parallelism. So here's an alternative. If you say cosine of a SIMD of float, and the SIMD of float allows any number of elements, 1, 2, 3, 4, 5, that is a host of functions, and now the caller can use whatever it needs and gets the parallelism out of it. And to be a bit more general, we want a concept that takes a T or a SIMD-T. Maybe you've seen that concept come up before. There was a GNU Radio process 1 T or SIMD-T. Yeah. Okay, now I'm gonna do some overview of what the SIMD type is and how it works. And I will try to do most of this, not via slides, but Compiler Explorer, some life hacking. I hope you can all read this. You don't have to understand it at this point. I'll walk you through this. Okay, for now, you can ignore everything above here. All we're looking at is the part down here. We have a function that returns something, and we just print that something using cout. Okay, simple enough. And what it does, it creates a float, returns it, and so we see down here it prints 1.1. Simple enough. Now I'm gonna do a simple replacement of the type, and then it recompiles the whole thing. And now we're returning a different type, right? We're returning a SIMD, and the cout now has to have an operator that does it. And basically this is just printing that SIMD, so it's iterating over it. So we're passing a SIMD here with a V and print it via this with the loop. It just subscripts into the V, gives us all the elements. And so we print down here a vector of 4 elements. Okay, that's 4 elements. Now if we look up here, I actually told the compiler I'm going to compile for a Skylake architecture. Now Skylake has AVX2 available. AVX2 has vectors with 8 floats. Why am I not getting 8 floats? The reason is that the committee wanted to be conservative for the TS. And I said SIMD should default to whatever the most common denominator of that target is. So a SIMD of float will be SSE for x86 64, and it's actually going to be a scalar for 32-bit x86 because that is like the common denominator. So if you want to have this scaling with whatever you're compiling for, you're asking for a native SIMD. So I changed this to a native SIMD of float, and now we have 8 results. But what actually happened here, so we initialized a SIMD that has 8 elements from just one value. I call this the broadcast constructor because you have this one value and it's being broadcast into all the elements of the float. You can also like default construct it. Default construction leads to 0 initialization. So I'm expecting 8 zeros there. Oh. Come on, Compiler Explorer. Yeah. Okay, so you can just initialize it. Like if you do int parentheses, you get a 0, right? So you can do the same thing here. We can also not initialize it and get all the problems that leads to, so if you don't initialize a float, you don't know what you're going to get. We're likely to get zeros here as well because typically everything is somehow initialized first. The stack is zeroed before the first use, so you would have to put data on the stack to see something. But even then, compilers nowadays try to zero over the stack sometimes and make sure it doesn't leak too much. C++26 will even have that part in the language to ensure that you get something sensible and not leak any data. So these are the 3 simple ways we can initialize this. There's a next very important one because typically you have data as an array of floats already. Now how do you get that array of floats into your SIMD? So I have an array of floats right here. It's a C array. And I'm going to say So I'm giving it a pointer, right? Data as a C array is all decays into a pointer. So there's a load constructor of the SIMD, and that, yeah, you are right. There's a load constructor, and that takes a pointer and a load store flag. Sadly, in the TS, no one wanted to have default for the flag, so you always have to say what you want. You have to say, is it aligned? Is the pointer aligned to an element, or is the pointer aligned to a whole vector? So alignment means basically a multiple of the address, right? And I'm saying that even here. I'm saying align as 64. So that means the pointer data, the pointer value, the number, is a multiple of 64. Now, if you know your x86 instructions, this one up here says vector move aligned packed single position. Aligned. I said element aligned, not vector aligned. How did you know? Actually, the compiler is smart enough to know by itself. It says align as 64. The compiler knows that data is aligned. So just saying element aligned doesn't hurt. It's safe. It's not going to crash. Because if we say it's vector aligned, and then I'll put a +1 here, it's obviously not aligned, right? I took a line pointer and I come on. Nah. That's always the danger with Compiler Explorer. It's whoa, it's see, the compiler is too smart. It actually omitted an unaligned instruction because I said it's aligned and the compiler said no. Apparently it's too smart for me. Okay, let's try something else. So yeah, okay. The point I wanted to make, let's not try this here because it takes too long to compile. The point I wanted to make is if you say vector aligned, you are making a promise that if it breaks, leads to a seg fault. And these are often puzzling when you're then going through with GDB and say, where is my outer bounds? My pointer is totally valid. And yeah, it is. It's just not. You have to look at the address and then look at it in hex and see that it has enough 0 bits in the end. And then you know why it crashed. So just typically put element aligned there unless there's a very good reason you saw from benchmarking. Element aligned will give you, at least on x86, best performance anyway. Whether it says move U APS or move A APS, those two instructions have mostly the same speed on the machine. There is an actual difference whether the pointer is actually aligned or not because you get cache line splits or not. And these cache line splits lead to twice the number of cycles required for loads and stores. Okay. There's another constructor some people might expect, right? Let's make it a 4 SIMD. We can do this with std array, but we can't do this here. Yeah, sorry for error messages. They are. I would like to make them better, but the language doesn't give me all the tools. So this does not compile. And the reason why this does not compile is because it does not scale. Right? If you write this code, you don't know whether you're going to get 4 elements. It could be 1. It could be something else. And here for native, it's even worse. 1, 4, 8, 16. So what would be the right number of values to put here and how to interpret if something is missing or if there are too many? So instead of being able to do this, we can give it a function. And so if you don't know what a lambda is, that was introduced in C++11. I'm introducing the lambda with the capture syntax. Or is it failing? No, it's not. With the capture syntax, I'm not capturing anything here. And then I say, I take one function parameter, I take an int. The int basically tells me the index position in the SIMD object. And then I'm going to turn that into a float and return that, and that will initialize the according element with that index. And so I'm getting a vector 0, 1, 2, 3, 4, 5, 6, 7. This is actually a very useful vector in SIMD programming. Sometimes you need some offsets in memory, for example, and that's exactly what you typically have then. Now here's a curious and important thing, and I will show this in another example as well. If we try to return a double from this function, it should not compile anymore. So SIMD has, in comparison to the other built-in types that we have, a bit more safety built in terms of conversions. Conversions need to be value preserving. So if you go from int to float, that is not value preserving because float only has 24 bits in the mantissa. But if you go from int to double, that is value preserving, that works. You can typically not go from any floating point to integer because there are so many values in a floating point that you cannot represent in an integer. That doesn't work. So you cannot go from double to float, but you can go from float to double. And the same is true if we try to initialize with a broadcast. If I just put a .1 here, this will not compile because I'm giving it a double. And I'm just not going to wait for this. I need to put an F here. I make it a floating point literal, and then this compiles. This is typically more important when you do any kind of calculation, like times 0.5. This is something that sounds useful. But again, that does not compile, because what needs to happen here is you have the left-hand side and right-hand side of a binary operator, and the first thing you want to do is both of them should become the same type. So the compiler checks, can I convert the left-hand side to the right-hand side? A SIMD float to a double? No, does not make sense. Can I convert a double to a SIMD float? And yeah, you could, but do you really want to convert down from a double to a float without the user actually calling that out? So what happens if you say float times double is that the float becomes a double. So what do you expect? The SIMD float times a double to become a SIMD double? This is bad because of performance. We suddenly need twice as many registers. We lose a lot of performance in SIMD programming if we do that. So this does not compile. And again, you just have to add an F here to make it a floating point literal, and then this compiles. All right, all the arithmetic is probably the interesting part, but look at this, the compiler knows what I'm doing. It is not emitting a multiplication. It just loads one value from LC1. Where is it? LC1, LC1, there's LC1. So this is our, yeah, in floating point it's a 0.5. So you get all the constant propagation that's happening at compile time with the SIMD types. And where it didn't work, and I found it, I made sure that it somehow works, either by bug reports to the GCC optimizer or by workarounds in the library. So if you find any constant propagation ever that you think should work, write a bug report. It's a performance bug, missed optimization. Okay, and also importantly, let's just take the sign of this thing. So here's a slight curiosity. If you have a float, you cannot normally at least write sine of x, because that would be the C function. in C++, there's only a std sign function. So you would have to say std sign of x, but then std sign of x does not compile with the SIMD because that's in the std experimental namespace. This will change again with C++ 26 when it's become proper part of the C++ standard. But for now, if you want to fully qualify this, you have to say std x sign. But there is a sign implementation that, so there is an optimized implementation for sine and cosine. I did not come around to do all the other ones, so there's a lot of work left. If you ever want to do an exponential, talk to me first because I have most of the work done. Yes?
So by default there, with just sine of x, you're getting the double result, and then it's, why is it not complaining? Isn't sine of x going to return double?
No, that would be the C function.
Okay,
so
so
this is overloaded on all signs.
Okay.
So it takes a sign of float and returns a sign of float.
Okay,
SIMD float and returns a SIMD float.
Okay, thank you.
Just like the std sign. If you do a std sign of float, you get a float. But if you say just without qualification of a float, then it would convert it to double, yeah. At least in theory it should, but there might be strange things implemented in some cases. Okay. Let me go back to the slides and see what I forgot. So this is important information. So there is this size function as a static const expr function. Means you can call it directly on the type. You don't have to have an object. And it's a const expression. So you can use this in template parameters. The size is something that's chosen by the implementation, and it should always depend on the compiler flags you pass. And for most targets, this relation holds, that there is a certain size of the register, and then you have to look at the size of the element type, and that determines how many elements you get. So there will be twice as many single precision floating points in a SIMD than double precision. Similar for integers, but this is not something you should rely on without at least a static assert, because there are special architectures out there, like for example Intel's Sandy Bridge, which introduced AVX just for floating points, but not for integers. I mean, the register is there, but the instructions are missing. Okay, so you saw the SIMD type. I did not mention yet that it has this second template parameter. I will just come to this. This first template parameter is allows all vectorizable types, which in the TS are all arithmetic types except bool. So this also includes the character types. It means you can vectorize strings right away, and wchars and whatever. We don't have bool there because we have a special type for this. It's called a SIMD mask. It's basically supposed to behave like a bool, but in contrast to bool, we need to have many different mask types. There are different ways of storing this in a processor. Some of them are bit masks, some of them are full width vector registers, and of course we have all the different SIMD widths. And then there's this ABI tag parameter. And this one is hoping to help you with a lot of headaches. Because consider you would compile one file with march equals something old and the other one something new. And then you have a function with the same name, with the same type, and the type, if it has the same name, the linker says, well, yeah, I can link this. And then you run it, and you get garbage or segfault or whatever. But by having this ABI tag, I can tell it, yeah, this is actually a different name. Even though in the source code you just wrote the same name, underneath it's actually different. And then when you link it, the linker says, nah, those two are not compatible. And then you go back and figure out how can I talk between those translation units. And there is an ABI tag in the TS that's called fixed size, which you can use for communicating between different ABI, between different translation units and also potentially over the wire. I'm not going to get into that. So we've seen this. So I talked about the loads. We also have the stores as the opposite to that, to go from a SIMD into a given pointer. Again, you can say element or vector aligned. All the arithmetics, I showed this before. Yeah, let's do the compares. All of the operations that I've shown, they happen element-wise. If I put do and plus, it's per element in the SIMDs. And I do the same thing for compares. So that means if I compare x less than y, I get multiple answers. And you cannot say if multiple answers do this, otherwise this, right? It's many. So what you can do instead is you compute the result for all of them and then say where this is true, do the assignment. So that's branch-free programming. It's conditional assignment. It's kind of like the question mark operator in a sense. Sadly, I can still not overload question mark, but I have a paper on this. And the other important thing you can do, whenever you have a collection of things, you can do a reduction. You just have to say how you want to reduce it. And so for Booleans, you want to be able to say all of them true, any of them, or none of them true. Back to that where function, you can think of it basically as if per element is true, then per element do the assignment. And this one supports not only plain assignment, but all the compound assignments, so plus equals and so on. Permutations are not part of the TS, but I copied the paper that is progressing towards C++26 into the VirSIMD implementation, which is a third-party dependency of GNU Radio, so you have that available. And there's a SIMD permute function in there. And what you do here is you have a similar problem as with the initializer list. You cannot say, well, these are the 4 indices on how you should do the permutation, because you want to be able to scale to different vector width. And so instead of giving a fixed number of indices, you'll give it a function where, given an index, you compute the other index of where to go. And then this function in this case just swaps all the neighbors. And important here is, in order to produce efficient code, we need in the instruction this 177. It needs to be coded into the assembly, so it needs to be a constant expression. This lambda will be at compile time completely computed, and then the compiler figures out, yeah, I have to encode 177 for that specific permutation here. Reductions, I mentioned them for masks. There are 3 more. Population count, so how many are true. Then find first and find last bit that is set. Basically, what's the index of the first true, what's the index of the last true. And then there are also reductions for SIMD, which basically work like the std reduce we already have in the library, that where you can pass any range. You can consider a SIMD being that range here. And so if you call reduce on an X, it sums up all the values. You can give it a different function for the reduction function. But we can also mask it, so we can say reduce where X is positive, only those values you should sum up. The functions for reducing to the minimum value and maximum value have a different name. That's mostly for technical reasons. This is going to change in 26. And that is sometimes quite useful. So if you do searching, that happens that you're looking, for example, for the smallest thing in a big array, and then you do all the minimum reductions, and then at some point you decide, okay, here it is, and then you wanted to return the index of that thing. How do you return the index of a value you just found? Well, you take that value, you compare it again with the SIMD you just looked at, so you do this comparison equals. That will give you a mask. Now you ask for the first one with that index, that where it's true, you get that index, and that is your position. Typically, the implementation of such a reduction is a tree reduction. And in terms of performance, keep in mind that this is not the full speed up, because when you're doing the tree reduction, it gets basically smaller and smaller in terms of the parallelization that you do. So if you have something big that you want to reduce, don't take a SIMD, reduce, SIMD, reduce, SIMD, reduce, and then sum them all up. That would be like wasting so much. Take those SIMDs plus the next, until you have only one SIMD left. So accumulate in a SIMD and then do the STIT reduce on the SIMD in the end. That's going to be so much faster. We've talked about reflection a bit before. I want to do something here with SIMD as well. So if you work just with floats and doubles, SIMD in the TS works fine for you because you can just replace it. But most of us have more structured data. And you do it as well. You have complex, at least, real imaginary. And at this point, it's not there. But very simple things, like you can define an aggregate like the point here, and then say SIMDice that thing. It's a meta function that produces a new type, which is kind of equivalent to a structure that has now a SIMD float of these three. Sadly, they are not called X, Y, and Z anymore because I don't know those names, and I especially cannot recreate those names. This will hopefully happen soon in standard C++, but not yet. So for now, what happens is you get kind of a tuple that has a SIMD interface that you can use. And this is already happening in GNU Radio under the hood. So SIMDice is used in there if you ever have a sample type that is an aggregate like this, and you are asking for SIMDs, you're going to get these SIMDiced meta transformed types.
Excuse me, so in the actual implementation, is the fourth field or whatever padded out to zeros in these cases? Or, I mean, I'm basically backing the struct into the...
So you mean the second struct?
Yeah, well, it's...
Yeah, you don't need any padding because each...
Sorry, this is the array of vectors versus vector array conversation, okay.
Yeah, so this is actually in between. So if you would have an array of points, that would be your array of structures. And now if you create these point V's and make an array of that, it's actually an array of vectorized structures. So you did not do a complete transformation to a structure of array.
Okay.
Okay, there is documentation. So the TS stuff is directly on CPP reference. Yeah.
For the last slide still, is this also useful if there's types that have different native SIMD sizes? So if you have a double and a float, then...
Yes, so that works. It uses some heuristic of what you probably wanted in terms of width, and it will have to use the same number of elements because otherwise that doesn't make sense. And so one of them has to either use double number of registers or 4 times or whatever. But yeah, so you can have that mixed. You can have even have it nested. So if there's another structure inside, it will just recurse and transform all of these. Another thing to mention, and this is documented, it's basically documented here how the SIMDice works. If you here give it a template, type name T point, and then say T X Y Z, then I'm going to do something different. And when you instantiate that with a float and then give it to my SIMDice point float, I'm going to make that a SIMDice point SIMD float, right? So you will have your names of the members still. With some checking that it's doing the same thing as it would otherwise do. Like if you have a T, X, Y, Z, and then a float something, that wouldn't work anymore, so I'm guarding against that. Okay, that's documented just all in the README, all the extensions on top of the TS. Time. Okay, let's do some signal processing. You all know signal processing, so we can go fast here, right? This is very similar to a process bulk function. We're getting in a span, we want to put out through a span, and I'm just implementing a gain here. So from now on, this precondition that the size is equal, we're going to assume that. And there's this simple implementation using a for loop. I've seen it all the time. And we can also do this using a standard algorithm. It's longer, but we're going to see how this is helpful in the end if you write it like this. So here we're basically saying go over this range, right into this range which starts there, and this is how you should transform each element. So we're calling it with a value out of this, and the return value goes into here. Okay, so how can we use SIMD in this example? We need to look for loops, because that's where typically all the data parallelism is. What the loop says is take this one value, do something, write it back, increment I, and only if you've done that, go to the next one. And this is kind of problematic, both to the compiler and to the CPU. Because you said, I'm going to read something here, and then write, and then read from a pointer. How does the compiler know that this next read is not what you've just written? It doesn't. So in C, there is a keyword called restrict, which mostly doesn't work as far as I am experienced. It does not exist in C++. There are extensions, __ restrict, and it still does not work. So the compiler assumes, yeah, there could be aliasing. So if you then actually tell a compiler, please vectorize such a loop, the first thing is, of course, it checks whether this range is actually 0. If it's 0, it goes out. The next thing it checks is, if it's trying to vectorize it, well, those two pointers I got here, are they far enough apart that I can take a chunk, store it back, and not override what I'm going to read next? So it does some pointer computation and then says, OK, I can take the fast path. And the interesting part here is that we encoded this into our loop, because we said, do this first. And when you're done, do the next step, because that's what we're saying with those semicolons, with those for loops. But actually, as the programmer, we knew about the parallelism all the way. It was clear to us that this is just data, and we just have to work on each of those samples. We don't care in what order. We just have to do it. So the simple way to do that is by saying, go over them and do it. We didn't meant to say, do it one after the other. We meant to say, just do it on all of them. And so we lost that information about the data parallelism. And it's right there. And we want to just do that by saying, OK, instead of a float, put a SIMD float there. It still has the problem that at this point, through chunking size, well, the compiler will see at compile time a fixed chunking size, so it has to assume there could be, again, load store issues. But on a higher level, at least for the developer, if you look at it and you just said native SIMD float, the native SIMD could be 1,024 values. If you go into a GPU, possibly even more. So at least on an abstract level, you encoded the complete data parallelism there, because you didn't constrain it to a certain width. So looking at this, where's our float here? It's just hidden in those temporaries. Let me make an L value out of this. I call it sample. And now just change the type from a float to a SIMD float. So this is what I recommend if you want to go from an existing code base to using SIMD. Just look for your data types, replace them with the corresponding SIMD type, and then go from there. So at this point, it's not correct. Because what we're doing here, we're looking at a single value. So this is a broadcast constructor. We're copying in all the elements that doesn't make sense. And even worse, down here, this does not compile, because now we want to say put a SIMD into a single float. That does not. You need a reduction to do that, and we didn't say how. So we need loads and stores here. So that's the load constructor. We're giving it now the pointer to the first element where to start reading from. We always have to spell out element aligned. And then when we're done, we need to copy it out into the out pointer, again, element aligned. So this compiles. Do you see what's missing? Yeah. You're one step too far, actually. Yes. We have a plus I still. So we still go sample by sample, and we compute every sample multiple times now. This is not very helpful. So the next thing here is how we go about the increments. We now go by the number of elements in the SIMD float. And as you correctly mentioned, there's undefined behavior in here. The bounce check is not right. Right? We don't know at this point that the size is a multiple of the SIMD size. So if you consider size would be 7 and the SIMD size would be 4, that's an obvious out of bounds. So we have to change this condition. For example, by saying, okay, if you go another SIMD size further, that's got to be less equal, and so on. Okay, so we're running out of slide space. This is no fun. And actually, okay, let's do something here. This is recommended practice from my experience, that you don't go all the time with saying SIMD float, and or more explicitly stdx SIMD float. Just put a float v somewhere. And then if you ever do mixed precision, this is the place you want to define all of them. Then you say float v is my workhorse. And then I'm going to do a double V that has the same number of elements as the float V. And then mixed precision becomes easy. And then if at some point you decide, well, maybe I should try the other way around, that the double V defines the size, then this is your only place where you change that. And then all over the place it still compiles, you can do the mixed precision stuff. Okay, so we have that shortened, that helps us a lot. And I took out the I equals 0 out of the for loop so that we have information after the for loop what is still to be done. And so we have to write another for loop to finish with the rest that we failed to put into a SIMD because there was not enough there. So we call that an epilogue in SIMD programming. Am I asking you to, from now on, just write 2 loops instead of 1? There are more possibilities. You can also do this with a recursion and then go from SIMD to half SIMD and further half and so on. Many possible approaches of how to do that epilogue. And if you decide, well, another one is better, and you go over all your codes and change all your epilogues, you're going to be so not happy and curse me. I have good news. I don't like this. So I implemented all of this in GNU Radio for you. Right? Just implement process 1 and you're good. So the thing we just saw, all this stuff here, you just have to tell me this. And the rest GNU Radio does for you. It does the epilogue. It does all the handling. Typically, it doesn't need to do an epilogue because you tell it in the port that you want a power of 2 values. So it knows I'm starting from a page-aligned buffer pointer, and I'm going in chunks of 1024. Never gonna need an epilogue, right? And so you don't have to do that, and the core knows it. It has more information than the block has. And that is why the process 1 is so interesting, because now you're saying, I can take a float, I can take any SIMD float, all I have to do is multiply with this gain, and however this is chunked over the memory, I don't care. GNU Radio, do this.
Thank you.
Yeah. Yeah, I didn't plan on implementing SIMD there. I was doing something else, and I saw, hey, this is such a good fit. I just have to do this. I can't stop myself. You don't have to do this as a template like this. You can also overload on a float and a SIMD float. The thing is here you still have to allow different ABI tags, because in case it wants to do an epilogue, it might want to do smaller SIMDs, and then you need to be able to accept different SIMD widths. I would recommend don't do this unless the code is really very different. And it can be different if you want to have lots of if statements in here, which are not going to work here, where you need to do branchless implementation using the where function. But you could also use context per if in such an implementation. There's another approach. So if you have to implement a process bulk, then start from this std transform implementation. And you can always, there's always this implicit execution policy of going sequentially over this. Spell it out. And then there's this minor tweak. You change the execution policy to ver execution SIMD. So that's part of the ver SIMD library. And what it does is exactly what I just showed. It does this for loop, chunking the SIMDs, doing the epilogue. And then this is why you have to put an auto here, because it will give you SIMDs of different sizes. So you can do that as well. And I implemented for each transform, transform reduce, and a few others. If you need more, write a feature request. I wanted to, how much time do I get for live hacking? Okay. I think this is interesting enough that we should look at a few options here. So, because you always also wanted to see how I do some of the analysis performance-wise. So this is me and my Vim, and I have a plugin that you can find on GitHub. There's in the exercise link that is on Indico, there's also a link to this Vim Compiler Explorer plugin that I'm using here, but also other ways of inspecting this are documented there. So this is the transform that I just showed on the slide. And if I compile this, I'm going to just quickly go over this first part. Basically here is where this gain, which is a single float, is broadcast into the YMM1 register, which is 8 values of floating point. And then after checking whether it can do so, it goes into this loop. So it's a multiply of 8 floating points, loading from the in pointer. And then the result, the YMM0, is stored back. That's the move double quad unaligned. Stored back to the out pointer. And then it increments this A register by 32, which is just the step, right, for the next, which is added to those offsets here, the in pointer, out pointer, plus this offset. And then it compares, am I done? And otherwise loops. So this is the loop that comes out of this first for loop doing this. And now there's LLVM MCA. So up here is the call that I just did. I called LLVM MCA on the code that I just highlighted here. And so what this does, it starts with, okay, I simulated 100 iterations of what you just gave me. And it said, I found I had to execute 500 instructions, and I needed 139 cycles to do so. There were 700 micro-ops. So if you're not familiar with that, every instruction is actually not executed. It's turned into micro-ops, and those are executed. We ignore the micro-ops for now, but we see micro-ops per cycle is 5. That sounds good. And instructions per cycle is 3.6, also a good high number. Whether it's actually good, I don't know, it's high. And so there's more information here. You can try to dive deep. So it tells you about all the instructions, what are the micro-ops, the latency. Latency here is high because it's loading from memory. If it's actually coming from L1, it's not going to be that high. this MCA is not going to know where it's at. But if it's L1, this is just full throughput. You can do 2 loads per cycle of SIMD registers on x86. And only 1 store. So we actually store limited here. Because we can also do 2 multiplies per cycle. It's the store that's going to limit us. If we go further down, there's more analysis. It tells us on which execution ports these instructions are likely to be scheduled. And here we get a timeline analysis of when the instruction is decoded and then put on the execution unit and when it retires and so on. And you see the dependency when it does the iterations, how you have this dependency on A. And there's further analysis down here on the average wait times based on that timeline view, and it tells you how many executions, average time spent, and so on waiting and so on. Okay, now this is hard to interpret, if you ask me, but if you stare at it long enough, it's useful.
On this particular machine, does the hardware prefetcher have enough buffering to fetch from like DRAM all the way through, or from L2 to 3?
Yeah, this is actually not doing enough work. So if it's way out of L1, L2, L3, performance is going to drop down a lot. I'm going to show a benchmark in a bit with a very similar one where you see that. But let's do something here in terms of ILP. We saw the effect of ILP before. So my execution policy here, the SIMD execution policy, has policy modifiers. And so I'm going to say, I modify the behavior by unroll this by 4. Loop unrolling by 4. Okay, so what do you expect? This is what happens. So this is our main loop now. We see 4 multiplies and 4 stores back into out, just to compare and jump. And up here we have the modification of the variable. And it's actually not doing an in pointer plus anymore, but it's now moving the in pointer and the out pointer. The compiler decided that might be better. I don't know why. So we can try to analyze that. We see way more instructions. Total cycles. IPC went down. It's hard to interpret. In the end, it's faster. So you also need to benchmark this. Kind of the reason why IPC went down is because notice that we had this loop overhead. We had the addition of the A register, the compare, the jump, and only 2 of those instructions of the whole loop were doing the work. And now the ratio is different. And now we're actually stalling on the store throughput. This is limiting it. And so since that is limiting our performance and we have way less other work to do, the instructions per cycle is going down, while the whole performance is going up. So don't just look at that number and get it up. You need to understand what's going on. And benchmark, benchmark, benchmark. So again, you can try to analyze this down here in the timeline view and how it's waiting. We're not going to dive deeper. So there are more modifiers that you can play with. I just, in the last days, implemented assume matching size, which was fun. It basically says, assume that the size of the range you're going over is matching the SIMD size in terms of multiples. So this got nicely short because the epilogue is gone. And you get safety. You get safety here. So the first thing it does, checks for 0. So if it's 0 size, it just directly returns. Then the next thing, so this is an AND. It checks whether it's actually true, your assumption you just gave me. And if it's not true, it's jumping into this cold region down here and it's calling UD2. If you ever saw UD2, it does a trap. So if you're, it's kind of saying, get me into the debugger, please. Otherwise, it's, I think, a sick bus or so. So you have some safety here. And to there is.
I have a question.
Yeah.
With contracts, if I can guarantee the calling function that this condition is met, will the second if vanish?
What do you mean in the second if?
Well, the epilogue, the check. When I know,
Yeah.
when I give by contract, I say by this function is designed to meet this criteria.
Yeah, so C++ contracts as proposed for the language will likely not do that, because there is a lot of pushback to the idea of contracts leading to assumptions. So the idea is that contracts only add safety, but do not add optimization opportunities for the compiler. So my answer is likely no, even though I think it would be interesting if it's a yes.
Static asserts, would they?
No, static asserts not, but an actual assert, yes.
No, if I would put, if in my code I have a static assert before that by compile time ensures that this case will not happen.
You cannot assert that at compile time, unless it's a std array.
Yeah, for example.
Yeah, for a std array, but then that check would also be gone. The compiler would see that this is 0.
Okay.
I actually, so okay. Let me go back to this fun one here. Just have to mention my heroes. If you see this a function up there, it takes an iterator, turns it into a address, so a pointer, and then says, assume that pointer is aligned. Now the compiler thinks all the pointers are aligned to 32. Now what that means, if the begin and end are both aligned to 32, yeah, it must be a multiple of the SIMD size. Right? So I tried whether that optimizes correctly, and it did not. So I wrote a bug report yesterday to GCC, and like an hour later, yeah, assigned to me. That should be simple. I will fix this. I love it when I write missed optimization. So Richard Biener, one of my heroes at GCC, always implementing my missed optimizations. But anyway, the one thing you can see here now, I added this assume aligned, and you do not see it on the mul.ps because that does not change, but you see it on the store. Now it's a move APS, so aligned store instead of an unaligned store. So the compiler can see this here by just, if it knows the pointers are aligned, it does the right thing. Okay. But I wanted to show another feature that I implemented. So this is a span. What if we create a subspan of 17 elements? And then we say, assume matching size. Compiling. Oh, does not compile. So this is something I implemented in VerSimD. I've showed this before in GSI in our C++ user group. A check of the preconditions that can happen at compile time if the optimizer sees it. So you have a bit of control over how the preconditions are checked. Again, this is documented in the README of VerSimD. And so here the optimizer can actually see it has 17 elements in the subspan. You just told me it's a multiple of 8. I can check this in the optimizer, not really at compile time. So the front end doesn't see it, but the optimizer sees it, and it throws a compile time error, and it points us right here that this is going wrong. And you can soften this, and then it compiles into a warning. It's actually still an error. Yeah, whatever. That's live hacking. Okay. So the idea is that if it doesn't see it, so we're going back to this. We're still saying assume matching size, and we saw before that. Why is it not? No matching function. Okay, let's just go back to this. And we saw this before, that it implemented this, this check and the jump down to the UD2. You have more control about what happens there. So if we say check preconditions 1, then it's actually just deleting that branch. So it now says built-in unreachable instead of built-in trap on that point. So you're saying, really assume this. Don't even check. So we get shorter core code, but less safety. So the default of VirSimD is this 3 where you get a trap. You can go further. So this is errors at compile time and information at runtime. So at runtime, it will actually print, at this point in your program, this is wrong with those values, abort. So you have more debug functionality. And I'm trying to implement this for all places where there are preconditions, basically undefined behavior. And so you have a better way of debugging this. My time's up. Okay, just quickly to the benchmark. This is very simple. We're just going over a sequence modifying in place with a plus. We have these, so we have unseek in the standard library, which says kind of vectorize this as a loop. And then I have SIMD on the other hand. Okay, benchmark this. Very simple implementation, standard C++ 02. That's our performance. Now, if I put the SIMD execution policy, that's much better. Now, if I take the standard for loop and put an 03 there, please vectorize this for me. Okay, that's nice. For unseek, it also gets. Why is unseek slower than the normal for loop? This is just embarrassing. And then with SIMD type execution policy, it's still a bit faster. So the 03 did something more than just vectorize. It did something that also helped the SIMD execution policy. It's probably doing unrolling. But I can say unroll by myself. And you're seeing this line up here. That's the theoretical maximum store throughput of that machine. So we're reaching the maximum. But then in the end here, it breaks down because the range just gets so big that we're not in L1, L2, L3. And so that starts to dominate the performance, and then they're all the same. But in general, in GNU Radio settings, you would be in small buffers and wouldn't have those huge buffers. But yeah, this can be limiting. Just to mention here, I think the important part here is in comparison to loop vectorization. With data parallel types, you have the control, you have the composition. We were able to say, well, this is how we want to go over the memory, and this is what we actually want to do with the memory. And this composition of these two, now I can pick and choose how I want to go over the memory while not changing what I'm doing. I can change what I do without changing, and that is very, very helpful. Okay, now a bit more GNU Radio and merge blocks and how I actually came to adding SIMD to the whole thing. We have an Amdahl's law problem. So if we optimize everything out of the blocks, at some point you're going to see speed up for the blocks, but not for the whole system. In other words, what's said here, the overall speed up of using SIMD, the whole flow graph may still be frustratingly slow. You don't get that much speed up because we had great improvements of throughput and latency per block, but because over time we have to invoke the block, process the samples, invoke the next blocks, process the samples. What happens here is the block writes to memory, scheduling happens, you have the buffer management, you have to avoid over and under runs with the circular buffer. Then the next block reads the input from memory, you probably have some cache memory latencies, and then the whole thing happens all over again. So we still have overhead. And to get rid of that, you have to write your whole application as one loop, right? Then you could just, doesn't have to go back and forth all the time. I have a better alternative. Let's just use the results from A immediately when with B and skip this in between. But this requires the connection at compile time. But it does not require us to implement a new block that merges the functionality. Right? If you have a block and you just need a gain on one of the inputs, copy the whole thing and add a new parameter just to put a gain there. Copy and paste programming maintenance, this is a nightmare. But for performance, yeah, you might want to consider this otherwise because you have this buffer in between. It costs you extra in performance. But if you can just at compile time say, merge a gain onto that input port and it comes at no cost at all in terms of performance because typically that gain is lost in all the other work. It's instruction level parallelism. It just consumed. It's for free to add a gain wherever you need it. And so you can write blocks without gain on every port. You can then later add them. So how this works is instead of this timeline, we want to get rid of this and invoke A, process the sample, and then B, with a good chance of those computations actually getting interleaved. And at least for now, a mergeable block implements process one instead of process block. And here, one, again, for the SIMD case, means one object, not necessarily one sample. So it can be a SIMD object with multiple samples. So a better picture looks like we're going from this, where we have the invocation calling this work function, which does the loop over the process one functions, and then going to the B work loop over the process one functions, into a new type, the A plus B type, which now has a work function, which does a loop over this. And so it calls the process one function, and that's the return value of that goes directly into the input of the other one. And if those functions are inlined, this is merged into a single process one function at compile time. And you get all the optimization you could ever get. This is writing the whole thing as one loop. You can't do this any better. Right? The merged block is this efficient loop implementation that you would otherwise do if you don't have. Sorry, what?
Until you run out of L1.
Not necessarily, no.
I mean, because all of a sudden you start getting stalls. I know that you're running on monstrously big Intel hardware, or you don't even, you never care. You've got like many, many megabytes of cache.
But no, what's actually happening here is this work function loops over the input. And now instead of doing little work per one sample or per SIMD of samples, you do a lot of work. So you
I'm
keep your
iCache, not data cache.
Yeah, okay, iCache.
iCache.
Yes.
iCache is like is on the order of L1 iCache is on the order of like 16K.
But in the end, the merged one should even be less total code size than if you have the individual ones.
Yeah, this is the one where I wonder. I mean, I don't doubt the total, but the question is, there's experiments to be done on relatively small cache sizes that just see what's the right answer. Do we have to chunk? Totally love that we can merge, but then I wonder, the tuning gets to be crazy because I might have to start merging or not merging depending on the characteristics of my cache, which doesn't look automatable right now.
Maybe I can explain a bit, because in the work function, each one of them also checks whether the validity of the required input samples and output samples is correct, and which is not done in the process one. So by merging it, this check is combined from the block A and B, and you execute once, so that reduces already the code size because you have only one check is a superset required for the overall input and output. And then the code that you actually inline, because you remove checks that are superfluous, becomes smaller.
Imagine you have a whole modulator, a whole transmitter, right? And you take the I'm merging it all.
No, I fully agree. I mean, like if you put the whole program, eventually it will not fit into L1. It will be chunked up and then has to be
Yeah, that's my point. And on some very popular, really high, shockingly great performance,
but
superscalar out of order, but small cache.
I think there's kind of a misunderstanding here what the problem is. I think the cache in any case would not fit the whole problem that you compile, whether it's multiple blocks or not. It is many places in your binary, and you will have to load into instruction cache in any case. So the main question is whether all these process one will be inlined into one thing, and that will not happen. The compiler will say, well, that's going to get too big. I'm going to make function calls out of this. So these process one boundaries, they will be still there. And that's a decision the compiler will do because it says, well, this is just getting too big. That doesn't make sense.
The compiler's not going to know the cache configuration, even by the March flag.
It does. It has all this information about all the CPUs, what is the cache size. So if you run GCC, it runs another program called CC1+.
Yep.
Try to look that in your process list. It has flags on L1, L2 size, and so on.
Okay.
And that is derived, especially when you run with march native. You will basically have a way of inspecting your system that way, because CC1+ will have that as arguments. So it is input to the compiler how big the caches are.
All right.
And there are more tuning parameters also with regard to how inlining works and when to inline and not to, because it's all heuristics, and the compiler can never do the right thing. So you can also tune that.
Okay, thanks. I'll check on the ARM.
Yeah.
Maybe they just don't. Maybe the GCC doesn't have all the data, possibly.
Possibly, but I think ARM people are submitting that, so it should have.
But there's no some ARM processors that are quite popular. There's no microarchitecture manual for them.
I just wanted to clarify. So right now, complex values don't work yet. So that was the point V example, right?
Yes. So complex is still on my list to find time for. Yeah.
Okay. And the other thing is, so in a lot of cases, you might have a resampling situation, and also in that case you can't merge, right?
Yeah. So if you have any sample rate difference, you would have to do a process bulk, and then at this point, merging doesn't work.
Okay. So
I can envision ways of still merging in some cases, but at this point, it's not there.
All right, thanks.
Okay, just a quick picture here again, how this merging improves things. So first, without SIMD, with SIMD we're going in bigger chunks, then we have per block this bandwidth increase, but this is where Amdahl's law bites. So we want to get rid of this buffer in between. And this happens when we do the merging. And it's hard to go any faster between two given buffers. All right, I need to finish this. So currently vectorizable types, all the arithmetic types other than bool, that's part of TS, depends on C++17. There's lots of work going on targeting C++26 and beyond. So we kicked out long double because it's useless for SIMD. You get a size 1 SIMD, and it's just a headache to implement and nothing else. So thank you for letting me drop that. And there's a paper. It is already design approved. It's just waiting to become part of the standard wording to add complex to the vectorizable types. So you would have a SIMD of complex. Not a complex of SIMD. So SIMD of complex means that your SIMD stores real, imaginary, real, imaginary. So when you do a load from an array of complex, it's a direct copy. Whereas a complex of SIMD would mean you have a complex where you store a SIMD of reals and a SIMD of imaginaries. And you see, you would have to permute on loads and stores. Both have their pros and cons in terms of performance characteristics. but at this point we're only targeting SIMD complex. And then we're looking at more like enums, std byte, in any other user-defined numeric types could become vectorizable types. So we do have prototypes, we do have a paper on this, but it's unlikely to make C+26. We want way more interoperability, direct conversion to from array and span, and any contiguous range where it makes sense. The masks are pretty much like a bit set, so that conversion should come. We want an initializer list for SIMD, even though I showed you the problems with it, so it's a bit tricky. And we're considering making SIMD and SIMD mask read-only ranges. There was no ranges back in C++17, so I couldn't even think about it. But when we do that, we have like std format just falling out because it formats a range now. And you can do things like vector SIMD t, just flatten that with a range adapter, and you have like a range of t. And that can make some of the problems very simple. Gather and scatter. Like, you can write this with an int right there, int indexes. You know what that means. But if I turn that into a SIMD int indexes, should it not also compile? I mean, the meaning is clear. So this is, gather and scatter is sometimes hard to use. The performance of this is bad, because gather and scatter performance on every machine is just like bad. So maybe we don't want to make it that easy, but yeah, so this we'll look at. So summary here, I think SIMD is for you because you care about latency and throughput. You want to express data parallelism, not think too much about SIMD, like when you focus on instructions registers. And the types enable you the separation of what do you do serially, what do you synchronously parallel, and where you want to do threads. I believe that the API of SIMD designs, guides you to do a scalable design in terms of scaling with the vector width. And there are now in VerSIMD high-level algorithms to make it much simpler to access ranges of scalars. And we have the high-level specialized abstractions with control where loop vectorization otherwise fails you. And as I mentioned at the beginning, you got an API and ABI for being able to pass many floats as one over library boundaries. And now you can start thinking about things like Volk, right? Libraries of that sense to become more accessible and more general. And if it becomes part of C++, this is a vocabulary type that the whole world can speak. And things become so much better to interoperate. Okay, just one more thing I have to show. And that is exercises. If you want to use SIMD, you should get your hands dirty. So there's a link on here. There's a link, should be a link down there on the Indico, yes. If you go there, this is where you land. So this is tutorial material that I created way back, so it doesn't use the benchmark facilities that are used in GNU Radio. It's built on top of Google Benchmark, but that is not an important point here because all the framework should just work for you. So if you want to set this up and play with this, basically just copy this to get started. You should have GCC anyway. You want to, for those exercises, probably install a new VerSIMD on its own. And here's your starting point for the benchmark exercises. And then this walks you through how to do benchmarking, how to do it wrong, how to interpret it, how to get the right numbers. So you need those optimization barriers for micro benchmarking, how to get that right. A bit about inspecting, like using Compiler Explorer, other ways of looking at the assembly and interpreting that. Here's a link to the Compiler Explorer I use in Vim, a very short introduction to the most important x86 instructions, and here, benchmarks of what you can try. Then going on with the benchmark, getting to peak flop without SIMD at this point still, and all the necessary information about how to interpret that. Why are those numbers the way they are, with links to the tables that document all these performance characteristics. Here's getting your hand dirty with SIMD itself. Basically what I live hacked, you can do this yourself and implement simple linear search. You can implement the for each that I showed the benchmark in a much simpler, less general way. You can try to generalize that. And then you can do more benchmark. Hit the peak flop and then linear search using SIMD. Compare that. We will see that glibc actually vectorizes this, but you can go faster than that. glibc uses an ifunc, so at runtime it has to dispatch, so it's always like a virtual function call. And since you are using SIMD directly, you don't have that overhead, and it's going to go faster. Here is a boilerplate with some strings, and you can get going right away. If you need more, you can do more and go up to interesting pictures. I expect you're not going to do this. But there are some solutions, at least here, so you can look at this. And also, when you clone this, there's another branch with results. So when you start with this, the main branch is like mostly empty. But you can also go to the other branch and look for inspiration, which is mostly, I think, what I put in here. All right.
Okay, thank you very much. I would say that we might take the questions during the coffee break, right? There were already lots of questions.
Yeah, let's maybe do a coffee break, and if there is interest for more discussion right afterwards, does that make sense?
Yes, right after. Exactly, yes.
Whoever needs to come to the mic comes for an answer.
Okay, so we'll just go for the coffee break. We are maybe 15 minutes late, so we'll try to catch up a little bit for this next session, of tutorials. All right? Thank you.
What time do we restart?
Sorry? So usually it was supposed to start at 15:30.
Yeah, so what time are we going to restart?
I would say, I don't know, maybe 30 minutes from now.
I think you just need to pick. Tell us what time.
Okay, so 15:50.